us till lunchtime also they'll meet us, so you can ask more questions. There are too many.
So it's a 15-minute talk.
Yeah, total is 1 hour. So distribute as for. And then at the end of it, after everybody is over, thanking is over, then you can, I'll hand you over the book. Okay. So good morning. I think today they are more spread out as your director wanted. So I guess this is a very beautiful hall, fabulous hall with good acoustics and everything. Today we have Professor Madhavan Mukund, who's the director of CMI, Chennai Mathematical Institute, giving the first talk, and I invite Professor Jayakumar Radhakrishnan to chair the session.
Good morning. My name is Jayakumar Radhakrishnan. Welcome to the first session of day 2 of the outreach program of the Resonance Journal of Science Education, Connecting the Dots. Our speaker this morning is Professor Madhavan Mukund. Madhavan is a theoretical computer scientist. He obtained his BTech degree in computer science and engineering from IIT Bombay in 1986, and his PhD from Aarhus University in 1992. He has been at the Chennai Mathematical Institute ever since, where he's at present professor and director. Madhavan is a member of the editorial board of Resonance, where he, among other things, makes the crossword. Madhavan has led various organizations that support academic research and teaching in India. For example, the Indian Association for Research in Computing Science and the Association for Computing Machinery, India Council, IARCS, and ACM India. Madhavan has made important contributions to several areas of concurrent and distributed systems, formal verification, and distributed algorithms. He has given a very popular online course on the design and analysis of algorithms on NPTEL. He will speak today on logic, automata, and program verification, a subject where he has made very important contributions himself. So please welcome Professor Madhavan Mukund.
Thank you, Jayakumar, and I hope this mic is working. Yeah, so I'll try to tell you a little bit about this area, which is broadly underpinning a lot of the work that I have done, and it's quite foundational in this branch of theoretical computer science, which connects some theoretical models, automata, with some very practical considerations, which is how do you validate that the program that you have written is doing what it's supposed to do. So that's program verification. I'll spend most of the time on the logic and automata part. At the end, I will give some quick connections to the program verification question. So what are automata? So automata are basically formal models of computation, and historically automata are actually older than what we now consider as computers. So they arose initially from the work of Turing, and later people like Kleene and other famous logicians and mathematicians formalized this notion. So this is a kind of abstract model of computation which captures the essence of what computation is about. On the other side, of course, we have all heard, if not studied, mathematical logic. So it is a language essentially for describing facts or properties, typically properties about mathematical structures, and it is a formal way of writing down things with an unambiguous semantics, and then you can ask whether certain facts imply certain other facts. So what I want to talk about today is that these two seemingly different aspects, automata theory, which is talking about computation and models of computation, and mathematical logic, which is really a formal language for describing properties of mathematical structures. So they are connected in a very profound way, and this work goes back to the work of J.R. Buchey, now almost 65 years ago. And so this is basically what I want to talk about today. But then I will also, so his motivation was to use automata theory to answer questions about logic. So in fact, this is a really fundamental, so computer science arose out of this question. So Hilbert in 1900, one of the questions he posed in his famous address was whether there is quote unquote in modern terminology decision procedure for logic. That is, can you write a program which will spit out all logically true facts given some axioms and some rules? And what Church and Turing tried to address this problem, and one of the challenges in addressing this problem was in 1900 there was no computer and there's no notion of what computation meant. And so essentially the idea of computer science, or theoretical computer science as we call it now, was to actually formulate this question of Hilbert precisely and answer it negatively. So there is a negative result saying in general you cannot do this. You cannot write logical formulas and expect to have an automatic kind of algorithmic procedure to derive all consequences, which is good for us because otherwise all of us would be out of work, because we would just, I mean, we're already almost out of work with ChatGPT, but with this we would definitely be out of work because you just have to run the algorithm. You don't need to have any ingenuity, but fortunately Turing and later Gödel and others showed that there are fundamental obstacles to doing this. But there are, nevertheless, logic is a very broad framework, right? So if you restrict your framework, then there are possibilities, and this is what Buchi was interested in. So this translates into the modern question, which is when you write software, how do you know that the software is working? And if it doesn't work, of course, it could be catastrophic. We have seen planes crash and so on. So this is something that you definitely want to validate. And again, the bottleneck in the general sense is that you cannot do this because of Turing's work, because it's not possible actually to write a program that checks another program, just like it's not possible to write a program that solves logic. But in restricted context, you can solve it, and this is one application of the work of Buchi. Okay? So let's start with these formal objects called automata. So an automaton is a collection of states with transitions. Now, you can think of this purely mathematically, so let me just show you an automaton. So you can just think of it as a graph like this. It's a directed graph. So the vertices or the nodes of the graph are the states, and the arrows between them are directed, and they have labels. So the way you should think about this as a computational model is that each state represents the state of your program. So if you write a program, I hope that everybody has had some experience of writing a program, but even if you have not, what does the program do? It keeps track of certain values, right? You start with certain values, you assign certain values based on some conditions. So at every point in your program, you have a certain set of values associated with the variables you are maintaining, and you are at some position in your program. So this is the state of your program. So if you have to manually execute it and you're on step 7 and you write down what the values are and somebody calls you for T, you can go away, have T come back and start at step 7, and nothing will go wrong because you have the complete understanding of what your program has done so far and what it's going to do for. So this is what a finite state automaton tries to capture in a limited sense. In general, a state could be an arbitrary value could be assigned. So if you are keeping track of numbers and all that, you have arbitrary number of values. So the number of possible states is infinite, right? Because the number could be 1, 2, 3, it could be anything. But we are restricting ourselves to finite state programs where the number of combinations of values are actually finite. So that is the abstract motivation. So we won't worry about what these states represent for now until the end of the talk. So here we have two states. They're called S1 and S2. And in this case, so the actions in our program will be, if you have a statement like x equal to 7, then what it will mean is that you would move to a new state where the variable x is assigned 7. So the label is the statement x equal to 7, and the new state is the one after the change of state due to the action you have just performed. So for us, our actions are just abstract actions. So we have, in this case, A's and B's. So we have a finite set of actions. So we have this graph. We have this finite set of actions which label the thing. So every time you perform an action, or sometimes in automata theory you read an action, it depends, it's given to you as an input, it's your program, right? So you read line by line in your program, and your state changes according to the rule, and the rule is given by this graph. So if you're in S1 and you read an A, you will go to S2. If you're in S2 and you read an A, you'll come back to S1. If you're in S2 and you read a B, you'll go to B. So that's what it says, okay? So we have these transitions, and now we typically want to perform a computation. So we start somewhere, so that's indicated by this incoming arrow, right? So this incoming arrow says that we start in S1, and there is also a notion of whether or not we succeeded, right? So there is some computations are good and some computations are not good. So that good or not good is indicated by the fact that this state, right, is colored green. I hope you can see that. and this is black. So in general, if you finish reading your input is some A, B, 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 some number of A's and B's, at the end of which you have jumped around this graph and you landed up somewhere. So if you landed up in a green place, you are good. That is, the input that you just read is a good input. If you landed up in a black place, it's a bad input. And then you want to characterize which are the kinds of patterns that you can recognize with these things. Okay? So, so we start on a, so we take a word. So this notation is just this set of all sequences of symbols. So sigma star is just a set of all A, B, any kind of finite sequence of symbols over the alphabet that you have fixed, right? And you accept if you start at an initial state, you read the word, follow the graph, follow the automaton, and if you end up in a final state. Okay, and this is called an accepting run. So in this case, right, just to understand what we're doing, so if you read an A, right, so supposing I give you an input right? So what will happen is that on the first A, right, you will go here. On the second B, you will stay here. Then again on a B, you will stay here because there's only one thing you can do on that state. And now on this A, you will come back. And now on this B, you will come here. So now after reading A, B, B, A, B, you have ended up at a green state. So you will accept A, B, 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 A, B. Whereas if it had been, for instance, something like this, then you would go here on the first A, right? And then you would stay here, and then you would come back, and then you would go again back here. Because on A, you don't have, none of these letters give you a choice, right? So you have to go wherever it takes you. So now if I read this, I end up in S2, so I don't accept this word. So intuitively what's happening is that every time you read an A, you go from S1 to S2, and every time you read another A, you come back from S2 to S1. So in order to go to S2 and come back, you have to read two A's. It doesn't matter what you do in terms of B's, because B's just keep you where you are. So what this graph is actually trying to capture is whether or not the number of A's you have read so far is odd or even. So as long as you've read an even number of A's, you are back at S1. If you've read an odd number of A's, you are in S2. So this will accept every input over A's and B's, which has an even number of A's, regardless of the number of B's. Okay? So this is the kind of analysis that you do with an automaton. So then you ask what kind of pattern. So you can recognize even. Can you recognize words in which you have odd number of A's? Perhaps. Can you recognize a word in which you have prime number of A's? Perhaps not, and so on. Okay? So there is a variation of this in which you can do more than one thing. So here is an automaton where if you are in the initial state, right, on an A, you have a choice of staying there or going here. So it's now an input may have more than one execution possible. In the earlier graph that I drew, if I give you an input, there is only a fixed path that you can follow. Here, if I give you, for instance, if I give you an input of the form A, B, you could stay here throughout. You could do two A's and a B, or you could do this, and then do this, right? Or you can do this, and then you're stuck. Because if you do the two A's, maybe I should label it this way. Right? I can either do the AAB by just refusing to move from S1, right? Or I can do the first A at S1, move to the second A at S2, and then take a B to S3. Or I can jump off at the very first instant, and then I get stuck. Right? So then I cannot finish the input. So if I cannot finish the input, it's not a run. If there is no transition for a given letter in a given state, I'm stuck, and then that's an invalid run. Right? So you have multiple runs, and now the rule is that it doesn't matter if there are 5 million runs. If there's at least one which takes you to a green state, you're good. In this case, we have at least one run which takes us to S3, we are good. Okay? And if you get stuck, as I said, that run doesn't count. So among all the runs which actually finish processing the input, you want to check if there's at least one. So this is very kind of, so this is called non-determinism, and this is very magical, right? So if in some sense you should think of this automaton as guessing how to process the word. What is the best way to process the word? And if it can make even one good guess, then you're done. So in this case, it has to guess that at some point it has to move from S1 to S2 so that it can reach S3 after that. So to go from S1 to S2, it needs an A. And after that, it can read any one more letter. So the second last thing it reads, it must be an A. Right? So the last letter can be A or B, but it must decide at some point that there are two letters left, and this letter is the second last letter, it's an A, let me jump. Till then, I stay at S1. So if it can make this, and so the idea is that this captures the essence of non-determinism. So here it will accept any word which has the second last letter as A. Okay? So now the interesting thing is that this particular automaton is non-deterministic, but it's not required that it be non-deterministic. You can build an automaton which makes unique choices by remembering the last two letters. Okay? So it keeps reading the word, and at the end of the word, depending, it just remembers the last two letters in the state. So if it lands up in a state where the last two letters was A followed by something, then that would be an accepting state. Right? But the problem with that is you will have many more states. So in general, with a blow up in the size, you can convert any non-deterministic automaton to a deterministic automaton by making it larger. Okay? So this is the conventional view of finite automata, but what we are going to do is something slightly different. Right? So what Bucchi wanted to know is what happens if we don't think of these sequences as finite. So finite sequences in some sense correspond naturally to what we do if you think of programs. We run a program, it does something, produces an answer. So it runs, so you might have loops and all these things, but it will run a finite number of steps and then it will give you an answer. So you're really interested in finite computations. Right? But Bucchi was interested from the logic perspective in infinite structures, as I will show you in a minute. So he asked, in the corresponding world of automata, how would it make sense to process not a finite sequence, but an infinite sequence? Right? So in a finite sequence, I said that you will take that sequence as accepting or a good sequence if you end in this green state. But now in an infinite sequence, you will never end. Right? So what is the interpretation that one should give for accepting or not accepting an infinite sequence? So there are many definitions, but this is the original definition due to Bucchi. So what he says is, think of these green states not as accepting states, but as states which you want to see very often, right? So you think of them, just call them something else. So you can call them good states or call them recurrent states or whatever. But the important thing is that in order to accept, you must pass through a good state. So you have an infinite sequence, so there is no end, right? So after every finite sequence of symbols, you have only passed through every state finitely many times. But if you have an infinite sequence, you must pass through some state infinitely often because there are only finitely many of these things. Okay? So that's a very simple argument you should try and convince yourself, that you cannot go through a finite set of objects infinitely often without picking one infinitely often. So you must pick at least one infinitely often. So what Bucchi said is, can you ensure that you pass through some green state infinitely often? If you do, then you accept. Now the question is still, how do you compute that in some sense, right? So it's, for us, it was easy for a finite word. We just manually traced out the thing and said, okay, we went from here to here to here to here, and we landed up here, and we accepted. Now with an infinite thing, you cannot do that, right? Because you cannot go round and round forever and then hope to check in the limit whether it gets infinitely often, because you can't mechanically do it by just running the automaton. So you need some analysis, but as a formal definition, this is what it means, okay? So, so here, for instance, is a variation of the first automaton that we saw, except now we are interpreting this over infinite words, right? In the original automaton that we saw, if you remember, we had a B here and an A here, okay? That's what I had shown you for the even number of A's. You go there if it's an even odd number, you come back if it's an even number, okay? But this is not that automaton, so I will erase this thing, okay? So now what this is saying is that you go to the right if you see an A, and you come to the left if you see a B. And you must be in S2 infinitely often. So the only way you can get to S2, if you think about it, is to read an A. The only way to reach S2 is to read an A. Okay? Every time you read a B, you move away from S2, and you can't come back unless you read an A. So if you want to keep coming back to S2 infinitely often, the only way to do this is to read an A infinitely often. Right? So in the first case, we said the only way to come back to the first S1 was to read an even number of A's. Here we are saying the only way to go back to S2 again and again is to read A again and again. Right? So this will therefore accept any input in which there are infinitely many A's. It makes no statement about the B's. There could be no B's. It could be all A's. Or there could be finite number of B's, one B and then all A's, or alternate A's and B's, infinitely many B's, but at least infinitely many A's. It could even be for every A there are 7 B's. It doesn't matter. Infinity is a nice number. You can do 10 times infinity is infinity, half of infinity is infinity, everything is infinite. Okay? So there is no statement about B's. It's only that you must see infinitely many A's. So now here is a slightly different automaton. Okay? So now what this does is it does the opposite. It says I want to be in S2 infinitely often, and the only way to get to S2 and stay there is to keep reading B's. Right? So at some point, and remember you can't get stuck. Once I read S2, I cannot read A's anymore. If I read an A after I reach S2, I'm stuck. And stuck is not good. Even in the infinite world, you have to keep on making transitions. So therefore, what this automaton will have to decide is that at some point I read an A or a B, and I decide that either I'm not going to see any more A's or this is the last A. So remember that if you have only finitely many things, at some point they will run out. Right? If your input has only finitely many A's, there has to be a last A. After that last A, you have no choice because your input is only A's and B's. So if you have an infinite sequence and you have only finitely many A's, it must look like some mishmash of A's and B's, stopping with the last A, and then a continuous stream of B's. That must be the structure. Right? So what this automaton is trying to do is guess when that stream starts. Figure out, so you stay in S1 as long as you're just processing a random sequence of A's and B's which you don't care about. But at some point you decide, and this is again this guess, right? You guess that I'm done. Okay? So you can guess, now you're flexible about the guess. You can guess at the precise point when you're done, which is the last A, or you can guess at any point after you believe there are no more A's coming, because you're allowed to move here from here to there on a B also, and say there are no more. So this will accept, because the previous one was infinitely many A's, this is accepting only finitely many A's, and every word, obviously, the number of A's is either finite or infinite. So therefore, these are the two complementary languages. But the interesting thing in this case is that this language, although I will not have time to prove it, in this model of infinite words, so in the earlier model I talked about that second last A, and I said that was a nice non-deterministic automaton, but you can make it deterministic by adding more states. Here, unfortunately, you cannot make this automaton deterministic even if you add more states, because there is a fundamental limitation to how this notion of accepting is defined. Okay? So this makes the world of these automata a little more complicated, because you cannot always assume that the automaton is deterministic. You must sometimes allow non-determinism. That is, you must allow choices which you don't have control over, but the automaton is allowed to guess in the most appropriate way if it wants to accept. Yeah? So basically the fundamental thing, the first thing that Bucchi observed was that in this model, unlike in the finite input case, non-determinism is strictly more powerful than determinism. So deterministic automata accept only a subset of the languages. But see, every deterministic automaton, if you don't make a guess, you're still, so non-determinism subsumes determinism. You don't need to make a guess. But if you're allowed to make a guess, you have more power. Okay? So this is the background of the automata. Right? So despite this, you can do things with these infinite state automata that you can do with conventional automata, right? So you can take two automata and you can construct a new automaton which accepts the union of this inputs that the two automata accept. You can do it for intersection. And more crucially, you can do it for the complement. So we saw that infinitely many A's and finitely many A's. So sometimes the complement requires non-determinism. And there is no direct way, unlike in a deterministic finite automaton, you can actually just exchange the final states. Everywhere where you used to accept, you reject, and everywhere where you used to reject, you accept. You do the same computation and you just exchange your decision. Right? But here you can't do that because your automaton may not be deterministic. So you have to check whether there is a run for accepting and that there is no run for the complement. So it's a little tricky, and this is really the heart of, from the automata theory perspective, this is the heart of the complexity of this model, is how to prove that it's closed under complementation. Okay? And then Bucchi was able to show this, and that's how he was able to proceed with his program of connecting this to logic, because these operations correspond very strongly to the logical operations of and, or, and negation. So whenever you do an AND of two things, you're doing an intersection. Whenever you're doing the OR of two things, you're doing a union. And whenever you're doing the complement of a formula, you're doing some kind of, in this case, the complement of the language. So he wanted to set up that correspondence. So this particular step, okay, is very non-trivial and very crucial to the discussion of this. Okay, and the last thing that we need, which is a technicality, but I won't get into it. But if you now take, say, supposing you have a word over ABC, okay, and you say, I'm not interested in the C's. Give me all the words where I take the word ABC and I throw away the C and I look at only the AB part. Right? Give me that language. Is there an automaton for that language if I know the language for ABC? Right? So this is projection. It's called projection. So you take a language and you erase certain symbols and you look for the language after erasure. Right? Is that accepted by an automaton? And that construction works both for the finite case and the infinite case. And this is again used in some kind of logical construction, which I will briefly mention maybe. Okay. So the most important thing, as I said, is that we need to check whether or not an input is accepted. Okay, and that's in general for a given input, it's hard to do. But the more important question is, does the automaton accept anything at all? So even for the finite state case, when I give you that finite word case, when I give you that automaton and I explain to you that this accepts even number of A's or this accepts the second last letter in A, that requires some insight. I mean, you have to figure out what is the pattern that it's recognizing. But the more fundamental question is, does it accept anything at all? Right? And does it accept anything at all is actually, if you think about it, is a graph theoretic problem, right? So you have this kind of a picture and you have some green states, right? And then you have some letters. So you're just asking whether there is any word that accepts. Now, any word that it accepts, you don't care what the letters on the word are. So you're just asking whether you can go from here and somehow reach there. Right? So is it possible to go from the starting state? So I should have drawn the starting state. So maybe this is the starting state. Right? Can I go from the starting state to the final state? So this is just a very simple graph theory. You just interpret your automaton as a graph, disregard all the letters and everything, and just say, this is the starting state, these are my final states. Is there a path from here to there? If there is a path from here to there, I can follow that path and read off the letters, and that input is accepted. There may be many such, but I'm interested in saying, is it empty or not empty? Does it accept anything at all? Okay? And it is possible not to accept anything just because you could have an automaton which, for example, looks like this, right? I start here, and it only has right? So if I start in the middle, I can only go left, I can never go to the right. So even though in principle there is a green state in my automaton, I cannot reach it. Right? So this is an example of an automaton regardless of what the letters are, which I can never accept any input. So the question is, how do you answer this corresponding question for this infinite word case? Because it's not just a simple case of reaching the thing, but you have to come back again and again. Right? How do you capture that? Fortunately, this again turns out to be a very simple graph theoretic observation. See, Bucky's definition actually says that green states, in general, green states occur infinitely often. But again, there are only finitely many green states. So if the set of green states occur infinitely often in a path, there must be one green state which occurs infinitely often, because it's not possible that every green state occurs only finitely often, because there are only finite number of them. So there must be at least one green state which must occur infinitely often. So what we want to do is reach that green state and keep coming back to that green state. Right? So we want this kind of a picture, sometimes called a lollipop. Right? So you want to start at your initial state, right? And somehow find a path that reaches any green state, such that I can keep coming back in one or more ways to that green state. And this will give me a word which, if I trace out the letters, will be accepted. Right? So this emptiness problem, as they call it for the Bucki automata, is decidable. Okay, so now let's do a quick switch over to this logic thing. So what Bucki was interested in was so as I said, the general problem of logic is that you can interpret it over arbitrary structures. So you can talk about a logic interpreted over, say, groups. You can talk about logics interpreted over graphs. So you can take arbitrary mathematical structures over numbers, over various, even among numbers, whether it's over integers, whether it's over the reals. So you have a number of interpretations of logic. And in general, the problem of answering questions about these formulas, are they true for all interpretations over this thing, are they true or not, is not something that you can algorithmically decide. But for certain interpretations which are useful, you can do it. So Bucke was interested in this particular logic which talks about properties of infinite sequences. Okay? So for him, an infinite sequence is essentially the set of natural numbers if you include 0, as all computer scientists do, in the set of natural numbers. So you start counting 0, 1, 2, 3. So you are looking at this particular infinite sequence. Okay? So you're looking at so this is a logic, a simple logic over natural numbers. Okay? And what you're allowed to do is to talk about the number and the next number. So you have a function which says that this is the successor. 1 is a successor of 0, 2 is a successor of 1, but you can't say 2 plus 3. Okay? And then you can say there exists a number, or for every number. But you can also say there exists a set of numbers, or for every set of numbers. So you have, this is the important question now which makes it slightly non-trivial, is that you can quantify over sets, right? And this is why it's called second order logic, right? And this monadic is a kind of technicality which I won't get into. So this particular logic is called S1S, right? It's the second order logic of one successor. So I'll give you examples. Right? So first, this is a formal statement of the logic. So you have to denote some object. So you start by denoting 0. So you have a constant 0 which is interpreted as 0. And then you have this function successor, right? So 1 is not part of your logic, but you can define 1 to be the successor of 0 because you have the function successor, right? And then you can define 2 to be the successor of 0 and so on. So you can write 1, 2, 3, 4, 17 in your logic. It's just a compact way of writing a long sequence of successors, okay? So you can write the numbers, but the numbers don't actually form part of the logic. They are just defined using successor of successor n times of 0. Then you can do or, not, and. Then as I said, you can quantify. You can say there exists a small x, okay? Or for all small x. So this means that x is an individual number. Or you can say there exists a subset, which I'll usually write with a capital number, okay? And now what you can do with respect to these things is you say, is this number in this set true or false? Or you can say, is this number equal to that number? Okay, so you have two things that you can ask about these things. So these are what are called atomic formulas. So these are the formulas. You build all these things and then you have to reduce it to true or false. So what are the questions you're asking, true or false? Does this number belong to that number? Does this number belong to that set? And do these two formulas denote the same sets of numbers? Okay. So let's look at some examples, right? So if I have two sets x and y of numbers, I want to write a formula which is true whenever the first set is a subset of the second set, right? And this is something which even if you want to define it formally in mathematics, how do you define subset, right? So everything that belongs to the first set must belong to the second set, and you can write that in this logic, right? So you can say, so this is, I'll write it big, right? So it says for every x, right? So x now, small x denotes an individual number. For every number, if this number belongs to capital X, it must also belong to capital Y. So this suggests that everything in X, everything in capital X is in capital Y. So this will be true whenever you substitute for X and Y two sets of numbers in which capital X is a subset of capital Y. Right? So this is the kind of thing that you can say in this logic. You can also say that two numbers, so I said that you can't, there's no arithmetic, right? So normally one way to say that x is smaller than y is to say that there exists a z such that x plus z is equal to y and z is not equal to 0. Right? So this is, but you don't have arithmetic. So how do you say that one number is smaller than another number? Okay? So this is a little bit tricky, but you can do it. So what you can do is you can first define a set to contain everything to its right. Right? So this says take a set Z which has the following property, that everything in Z has its successor in Z. So this said that if any element belongs to Z, then the number after that is in Z. But that applies to that number also. So the number after that is also in Z. Applies to that number. So the number after that is also. So this basically says that Z is kind of close to the right. Okay. So that's the first thing. So you say that for every Z which is close to the right, okay, if the number to the right of X belongs to Z, then Y must belong to Z. So pictorially, right, what we are saying is that you are at X and you take any set Z which contains this number, then it must contain this number, this contains this number, this contains. So any such Z must contain Y. Because if Y is bigger than X, it's to the right of X. So every set which goes to the right of X must necessarily contain Y. Okay? So these are slightly indirect ways of doing this, but you have to say that. And the last example, just to show you what kind of a logic this is how powerful it is that you can actually write down the principle of induction in this. So what this says is that if you have a set in which 0 is there, right? So 0 belongs to X. And again that same property that for every number in X, the next number is also in X. Right? Then in fact every number belongs to X. Right? So any set which has 0 and is closed under successor must be the whole set. Okay, and that's how you prove things by induction. You prove something for 0 and then you say if it is true for n, it is true for n plus 1 and therefore it's true for all n. Right? So you can define actually a kind of this version of induction in this logic. So it's a fairly powerful logic. Right? And Bucky's question was, okay, I write these kind of sets. So is this true? Is the principle of mathematical induction true? Right? That's his question. Because you can write it in this logic. The question is this true or not? Okay? Is it true that every set which contains 0 and is closed under successor actually must contain all the numbers? Right? So this is the question that Bucky wanted to answer. Right? So when is this satisfiable and when is it always true? Right? So now the connection is, he wanted to connect it to automata. So how do you connect this to automata? Well, the thing is that you want to interpret a set of numbers as a word, because automata process words. So what is this word? This word is just the characteristic function. That is, it has, the set is, it has one, so say the set of even numbers, right? So set of even numbers is 0, 2, 4, 6 and so on, right? If I think of it in terms of the overall set, where I've left out these numbers, I can write it as this is not there, this is there, this is not there, this is there, this is not there, this is there. So I can write a tick mark wherever the number belongs to the set, and wherever it doesn't belong, I put a cross, and I can equivalently represent this as a word with 2 letters, 1 and 0. So this is just a characteristic function, right? So it just says that the position is marked with 1 if that position belongs to the set. Okay? So now I will check, for instance, if this formula satisfies a set by running it on the characteristic function of the formula. So let's look at this subset, for instance, right? So, or let's look at less than. Okay? So for less than, this is what it should look like. So this is my X and this is my Y. Right? I want to check that X is less than Y. So X is a single element. So it should have only one position marked 1. Right? It's a subset of size 1. Y is also a subset of size 1. But the 1 in the Y should be to the right of the 1 in the X. So I should see a picture where if I lay these two sequences above each other, the X sequence should have a 1 before the Y sequence has a 1. So what will happen is my automaton will process these pairs. It will say, okay, for position 0, both of them say 0. For position 1, both of them say 0, and so on. And at some point, it must see a 1 on the top and a 0 on the bottom, which says it has seen the X. And later on, it must see a 0 on the top and 1 on the bottom, which says Y. And everywhere else, it must see 0, 0. Right? So you can draw an automaton. So this is an automaton which actually checks that. Right? So it keeps on seeing 0, 0. At some point, it sees the X. And then at some point, it sees the Y. Right? And once it has done that, it stays here provided it sees nothing else. So other than this one point where it sees 1, 0 and the other point where it sees 0, 1, it must see only zeros. So there cannot be any spurious elements. Okay, so small x must be a single one, small y must be a single one. So this was Bucky's insight, that you can actually convert these subsets of natural numbers into these infinite sequences over 0, 1 over the alphabet, and then run automata on this. Right? And this automata will accept if and only if the formula is true. So I won't go into the details because it requires some technicalities, but finally what you end up saying is that you can actually construct an automaton for every formula. So the automaton will accept precisely those 0, 1 inputs which make the formula true, and then eventually with this you get a decision procedure, right? So you'll find out that you can effectively check whether a formula is true or not. So finally, if you have a sentence which has no free variables, it's either true or false, right? So that amounts to asking whether the automaton has any input or not. So finally, the fact that we can check for emptiness of a Bucki automaton is equivalent to checking whether a formula can be made true or not. So this is the connection that Bucki established, showing that you can decide satisfiability in this logic by actually converting everything to Bucki automata and asking the questions about the automata. Okay. So just quickly, I will just talk about this. So the thing is that the way this translates now into our understanding of programs is that, as I said, we normally write programs which compute a number and produce an answer, right? So we take an x and it computes some f of x. But if you look at many computer systems that you deal with on a day-to-day basis, okay, such as your phone or your laptop or anything, it is also dealing with an operating system or an underlying thing which should never stop. So those systems that are running at the background of a mobile network or running the operating system of a laptop, so these are systems which never compute an answer. Instead, what they do is they wait for you to interact, right? You click something with the mouse, or you dial a number on your phone, or some signal comes from another side and it has to respond to that signal, right? So these are things where the system is never ending and it doesn't process an output, but rather it reacts to the environment. So this is a term which was coined by a very famous computer scientist in this area. He called it reactive, right? So these are reactive systems. They are systems which run forever, and their job is to interact. They don't compute, but they always have to give the right interaction. Okay? So now how do you reason about these kinds of things? So here is an example, right? So you have a typical system where you have some resource which must be shared. And so if two people print on a printer, you don't want the printouts to be mixed up, right? You don't want one page of this and then one page of that and so on. So you have to have some way of understanding that these things have to be, one has to wait for the other, right? So you can ignore the small code there, but you essentially have a system where if you want to print something, you have to say, I want to print, then you have to wait for the printer to be idle, and then you print. So if somebody else is printing, then your program has to wait somehow, okay? So now if you have one such program, okay, which is sending things to the printer, then it essentially goes through this cycle. It's idle, then at some point it wants to print, so it waits, then it prints, and then it becomes idle again, right? And there might be another such printer which does the same thing, right? And now when you put these together, you get a compound thing where depending on what each of them is doing, you have different combinations, right? But what you don't want is this state which is missing here. So you don't want a state which says, right? You want to ensure that you never reach a state where both of them are printing at the same time, because then the printouts are jumbled. So you can build this kind of this is nothing but an automaton. Okay, so you can build an automaton of this which just captures the essence of what these systems are doing, and then you can ask questions about this. And because these automata are processing infinite inputs, because these are reactive systems, they are really in this model of Bucki. And you can also frame properties about this, which I will not talk about because I want to give some time. So you can actually write logical properties of these systems, and then thanks to Bucki's theorem, you can actually solve these properties, okay? So you can ask questions like, they never access a printer. So every run of the system now looks like this kind of infinite word. And you want to say things like the access is mutually exclusive. That is, you never see print. Okay. You also want to say that if I'm waiting, so print is not being accessible is trivial. You never allow anybody to print. Okay, so that's also a valid solution to the problem, right? So you don't want trivial solutions where you just, I mean, this is a very, right, in many schools you don't want your lab equipment to be spoiled, so you put it in a cupboard and lock it up. It's a good solution. Your lab equipment will never be spoiled, but nobody uses it also, right? So that's not the solution you want. You want to allow people to print, right? But then you don't want to favor one over the other. So if some process is waiting to print, it must not be starved of the printer. It must not be that every time if 1 and 2 come, that you always say that 2 prints. Right? So these are all properties that you can request, you can state, and then you can validate whether it is the program that you have written and the model that you have built out of it using this automata actually validates this problem or not. Okay? So you can actually say all these things. So I'll just quickly say this. The only difficulty is that the complexity of this is actually, so if you have a formula of length n, it takes 2 to the 2 to the 2 to the 2 of height n in general to build, or the automaton that you build for it under Bucky's construction. Okay, so this is not theoretically very practical, but amazingly, like in many other things, there are actually practical systems which have been built on this. So it's not entirely absurd also to use this. But there is another alternative which is called temporal logic, which I'm not going to talk about, which gives you slightly better things. Okay, so what I'll do is now I'll quickly just summarize what I want to say. So what Bucky showed is that actually the original motivation of defining computability was in the context of answering questions about logic, but Bucky actually showed that there is a very direct connection of how you can model logic in automata and use automata theoretic techniques, right, in order to answer questions about logic in a very direct way. So this has been exploited a lot after this in this area of formal verification. So there is this simpler logic than this monadic second order logic S1S called temporal logic, which I didn't talk about, which allows you to talk about these infinite sequences. And these logics are quite heavily used now in the software industry, especially in domains where making mistakes is critical and to be avoided at all costs. So they actually validate that their systems satisfy these kind of properties, right? And so this is something called a model checking problem. So you give me a model of your system and ask me whether a property holds, and I can use this automata theoretic technique to actually validate this. Okay? So here are some references. So there's a very nice survey by Wolfgang Thomas, which is a starting point of all things, and I have a couple of survey articles also, if you're interested, which you can find on my web page. So I'll stop there, and I'm happy to take questions.
Questions? Just raise your hand and I'll bring the mic to you. Yeah.
Hello. Thank you, sir, for an amazing talk. When you said you can verify for an algorithm if certain properties hold, like how much complex algorithms can we use automata to verify?
Yeah, so that is a very difficult question to answer in general. So this is the kind of verification that follows from this line of work is actually very suitable for these kind of what you might call control kind of. So you're not really talking much about what is, so there's no data in this, in the sense that you're not validating that you're asking whether the system can print, but you're not asking whether the printer prints what you sent to print. I mean, whether data got lost or something like that, right? So you're not talking about values, you're only talking about the signals which are interchanged between the different processes to say you go first, I'll go second. So these are very restricted kinds of things. So these are useful for one class of verification. The other class of verification which you really want to talk about is when you write programs which manipulate data. So there are some models of automata with data, but in my experience, they are still very theoretical. They are not directly used in verification tools. But there are other approaches that use logic in a more direct way to say things like, at the end of the program, I want my array to be sorted. So that you can write out, saying for every position I and every position j, if I is less than j, the array evaluate I is less. And then you can ask what must be, and this is the last statement of my program. So what must have been the property before this to ensure that after this the array is sorted. So you can make these assertions, and then you can ask in a more traditional logical sense whether the initial assumption implies the assertion after the first statement, implies the assertion after the second statement, and then how do you deal with loops. So this is a completely different domain of program verification, which is not overlapping with this. But again, it's very open as to where it works, where it doesn't work, because it depends on the nature of the data. Because in general, it will not work, because that is guaranteed by the negative results of Turing and Gödel and all these things. So you have to try and enlarge it to, and in some cases, you have these so-called semi-distinct, either it will work or it will just go on forever and not give you an answer. So it's a challenging problem a lot of people are addressing, but there is no precise characterization of that.
And sir, what happens if we feed a finite sequence into an Buki automata?
Well, by definition, you cannot, right? You have to interpret the automaton as either this or that. So there are some logics and some models which are over a combination of finite and infinite sequences, but you will always have to give two separate. If it is finite, then this is what it means. The other thing that you sometimes do is that if it is finite, you just assume that every state has a self loop, or you can go to a state which just loops. So you can convert everything to infinite by brute force by just adding one dummy state, where if you actually stop, you go there and then you just sit there, right? So technically you can do it, but normally you don't do it.
Thank you, sir.
More questions? So maybe can I request you to comment on one thing? I mean, these are all young people looking for careers, etc. Now, the Indian industry, there is going to be automation at a big scale. We often see, after you land at an airport, the aircraft has not been assigned a bay because maybe both of them are waiting and still there is a bay available somewhere. So many things are being automated. Do you think the Indian industry is using techniques from the area of verification and logic to make its designs robust?
So certainly in some domains it is. So I know that, because a large class of, so these kinds of things, as I said, are typically most important in systems where the errors are critical, right? And traditionally, for the last, 50 years, there have been two outstanding domains for this. One is things like nuclear power plants, right? If you are writing some software which controls a nuclear power plant, when to shut down, when to do something, you don't want to make mistakes. Or the other thing is when you're controlling large vehicles like planes. So planes have been flying with software since the late 1980s. So if a plane does something wrong because the software has a glitch, then people are going to die. So these things have a lot of verification. And now the scary thing is that the software in planes is coming into cars, right? So the same problems at a smaller scale, but with equally damaging impact. Right? If suddenly you have sensors in your car, a sensor might decide that the petrol is over. You're on a highway with everybody whizzing past you at 100 kilometers, suddenly your car stops. Right? So you're likely to get hit by somebody. So these are all problems which, so companies which write software, and many Indian companies do write software for these kind of manufacturers, so they are very concerned about this. But, and the other side is electronics, because a lot of chips have optimized and they have subtle errors, and then chips have to be recalled if they're not doing what they're doing. So finally your software may be right, but it's running on the chip is not right. Right? So what the instruction that you ask it to execute is not being executed the way it should be. So chip manufacturers do a lot of this kind of stuff. So it is still restricted to these kinds of domains. People don't really bother too much. Unfortunately, we are all too forgiving, right? We say, oh, this app is not working, the new version will come, it will fix the bug. So this is the problem. When you have the typical, why does every app have to be updated every 2 weeks? Right? It's because they're constantly finding bugs. It's very rare that they actually give you something new to do. So the problem is that we are very happy with this world where things work sort of, but these are not critical, right? If your Amazon app gives you the wrong recommendation, nothing is going to happen to you. But we are kind of forgiving about this software bugs. but in some domains it is not forgivable. So that's where but I think it's growing. Everybody is realizing that there is a cost to shipping something with mistakes, and then especially if it's built into something, if it's in your microwave or your refrigerator and it does the wrong thing, the thermostat doesn't work properly, then it's a very expensive thing to fix.
Sir, I have one more doubt.
Two things actually. The first one, I might have got it wrong. Somewhere you said for stopping, it should have a second last, should be an A like that.
Yeah.
When you say it should know, a computer program running, I would have thought was something causal.
Yeah, so that is the paradox. So when you have these non-deterministic automata, they are actually making guesses without knowing the future. So it's a very powerful idea, but implementing it is, as you said, not very clear. And in fact, this famous problem in theoretical computer science, which is P versus NP, is precisely asking what is the power of this ability to guess, right? So non-deterministic polynomial time, which is what NP expands to, is basically saying, can I guess an answer and verify it in polynomial time? And nobody is yet able to show that this is a strictly more powerful technique than having to actually compute the answer in polynomial time. So this non-determinism is, I think, one of the, I would say, contributions in some sense of theoretical computer science, because it's not random, it is not probabilistic, it is like God-given guess, right? So some higher force is guiding you in the right direction with no intuition as to why that is right, without knowing the future. So it's a very powerful thing, and it's very counterintuitive. So it's something that, so that is the thing. So you can't explain it. That's just a definition in some sense. If a good guess exists, it will find it.
And in connection with that, this will not apply to quantum computing.
Yeah, so quantum computing is not quite the same thing as non-determinism, definitely. It's more close to traditional randomness in some sense.
And the other thing was, when you were speaking about that recurrent thing, and it sounded like fixed point and limit cycles.
Fixed points are more complicated because you're talking about an input which, like x equal to f of x. Here you're just asking for a path which repeats. So it's a much simpler thing than the fixed point. Yeah, I mean, those also arise, but this is much simpler than fixed point. You don't have to calculate any fixed points.
Thank you so much.
Just one last question. I mean, other than apps, we also see frequent amendments to laws which are made in parliaments, etc. So how much is this theory applied to the legal system?
I think a lot of people would like to see it applied to the legal system, but one questions whether it's actually intentionally ambiguous, right? That in some sense you need some, I think it's, see, if you are in any institution or any framework where you have to make rules, you will always find the moment you make a rule that a few weeks later there is a genuine case which does not meet the intent behind the rule, and then you have to make exceptions. So I think this is the problem of laws and all these kind of things. It is very hard to codify a universal thing which does not require exceptions.
But at least avoiding contradictions might be a favor.
Yeah, but then of course, yeah, when you have a sufficiently wide range of things, there will be contradictions. No, I think there has been some attempts to do this. So in fact, an amusing thing was once around 10, 15 years ago, somebody actually wrote to me saying he had seen some notes of mine on functional programming and he wanted to learn this language, and he was a lawyer in Germany. And he was precisely trying to do this. He was trying to use these kind of systems to try and codify, but I think it's only a small number of idealists, I think, do it. The rest of the people give up their hand, throw up their hands and give up, I think.
Any more questions? Yeah, let's thank Madhavan again. On behalf of Resonance, I've been asked to present Madhavan this book, Lilavati's Daughters.
Oh, thank you so much. So now I have bad news for you.
So now there is a, Suri
okay.
comes back. Yeah.
Thank you both. Thank you. Thank you for sharing. So I believe that there is a photography session below, outside when we have tea also, and there will be some further announcements, maybe, perhaps, yeah. You got it? I think these boys were there, so took the QR code, scanned, and it got it.
Sir, I do have a pencil, but I'm not sure if it's
You
compatible.
can just see whether it works.
It's not an Apple pencil.
Then it won't, I think. Apple is only. Only Apple will work for Apple. Please come, Angan. Call others also. As I said, Apple will not allow any non-Apple to.
No, no, my iPad is Apple, but the pencil is not Apple.
But how does it allow?
It works. It's like
Okay, that's
it's
nice.
an ESD app.
So did you write a mail to me? Not yet, no?
No, I haven't yet. I
okay,
didn't
good.
get the chance. I was
Yeah.
so tired yesterday.
Nice.
I will.
Yeah. So you went to the science. No, where did you go here?
Yesterday?
Uh-huh.
No. We just went on our own.
Oh,
we
you're
went
on,
to the
okay.
other departments. And I will write you.
Yes, sure. Can close the door. I think people will keep coming like that. Now, please come in quickly. Don't. Okay. So, welcome to the second session. We have a change in the next talk is going to be Professor Jaykumar's talk, but that will be followed by a talk by Professor Shabnam Iyani, which was supposed to be held tomorrow, exchange for this. So Professor Hema will speak tomorrow. After Jaykumar will be Professor Shabnam. So after that, we also perhaps plan to have another photograph here, if that didn't come out well or something like that. In case with the backdrop of resonance, just after the sessions are over, before we go for lunch. Okay. I will again announce, but right now let me welcome Professor Jaykumar to give this talk, and also welcome Professor Madhavan to chair this session. There are two talks.
So, welcome to this session. It's a pleasure to introduce Jaykumar. So Jaykumar has been at TIFR for many years and recently moved to ICTS, which is also a part of TIFR in Bangalore. His main contributions have been, of course, in a wide range of topics in theoretical computer science, but largely centered around probabilistic arguments. And I would say that currently he's the foremost expert in computer science, at least in India, and in quantum computing, which emanates from some of these ideas. But today he's going to tell us about the probabilistic method in combinatorics, I think. So over to you, Jaykumar.
Yeah, good morning. So I'm going to talk about the probabilistic method, which is a topic in mathematics. So I actually don't have a good sense of the audience. I've been told that it's largely undergraduate, but I don't know if undergraduate students already classify themselves as mathematics, physics, biology. So how many of you are mathematics students? Or is there such a thing? Yeah, okay, yeah. Okay. And how many of you are physics students? Yeah. Okay, all right. Biology? And chemistry? Yeah. Very good. Yeah, so we have a reasonable mix, and the talk that I plan to give is intended to be accessible to everybody, even the professors in the front. So, yeah, so if something is not clear, it's because I'm not being clear, and you should just shout and ask. Okay, all right. So let's start. Yeah. So the plan is, I'll tell you what the probabilistic method is, and it will not be, absolutely precise. I'll give you an example, then another example. And the last time I gave this talk, it was in Chennai. So I used this I'm sorry, this has stopped working now. So Madhavan, can you just give me your pen? Yeah. sorry. Yeah, so I think I need to sing this.
Somebody has yet another pen.
Yeah. Sorry, come to your talk. Yeah.
You have to touch this. Oh, sorry. Maybe that's what maybe you didn't know. You have to do this.
Right.
That's that. This one.
No. Okay, now. Yeah. Yeah. Okay. Yeah. So yeah, the last time I gave the talk, I used this Tamil word, but I assume it's also a Malayalam word. So yeah. So I'll have. Yeah. Okay. So drop it there. Yeah. Is there a orientation or? Okay. Oh, so it's working. Yeah. I mean, at least it seems to recognize it. Great. Yeah. Thank you. So I have a whole collection of pens. Each time I give a talk, I take home some. Yeah. Yeah. So all right. So yeah. Right. So this is what we do. So the probabilistic method is attributed to Paul Erdős, a famous mathematician, and he used it in a variety of settings. And to honor him, his country actually issued a coin in his memory. So yeah, so which country is this? So this name here. So yeah, so do you see this, Magyarország? Magyarország? No? Yeah, so yeah. Okay, so it's Hungary. Yeah? Yeah. So it's a Hungarian coin, and I don't know if you see this little theorem here, NP2N. Yeah. What do you think it says? So between every number and twice that number, there is always a prime number. Yeah. So actually, one of the shorter proofs or important proofs of this theorem was due to Ramanujan, but it's not Ramanujan's theorem. It's an older theorem, Chebyshev. Yeah. Yeah. All right. So that was just to warm you up. So the first example of the probabilistic method that I want to give, it concerns polygons. Yeah? Something we learn in maybe high school. So a polygon is a convex if the straight line segments connecting any 2 points lies inside the polygon. So for example, this polygon, if I put any 2 points inside the polygon and I connect them, the entire line segment will still be inside the polygon. So this polygon is convex. Yeah? But this polygon here is not convex. Why? Because if I were to choose the point here and connect the line leaves the polygon temporarily. So polygons which look like that, the one on the top, are called convex. Yeah, they're convex. There are no concave little niches like here or here. And the others, yeah. So we are, the first theorem I'm going to tell you about refers to convex polygons. Okay, so you have a good understanding of what convex polygons are. So the theorem is about perimeters of convex polygons. So what's the perimeter of a polygon? Well, again, I don't need to, sorry, something is wrong. No, I'm writing on this, it's okay. Yeah. You're going to the screen. No, that's okay. I have a hand. Yeah, thanks. Yeah. Okay, yeah, thanks. Good. Yeah. So, so the perimeter of a polygon is just the sum of the sides, yeah, sum of the lengths of the sides. So if you look at this polygon A, then its perimeter is 3 plus 6 plus 5 plus 4 plus 7, so 25, whereas this one is just 1 plus 7 plus 3 plus 8, yeah, 1 plus 7 plus 3 plus 8 is 19. Okay, so these words are familiar to you, you know what they are. Yeah. So here we have a outer convex polygon B and an inner convex polygon A. Okay. Yeah. And clearly the area of the inner convex polygon is less than the area of the outer convex polygon. I mean, that doesn't even need any state. Is it true that the perimeter of the inner polygon is always less than the outer polygon? So in this case, it seems somewhat obvious, but the inner polygon could have had many, many, many sides. Yeah? And could it be that somehow there is a polygon, convex polygon, which is sitting inside another convex polygon, but the perimeter of the inner convex polygon can be bigger than the perimeter of the outer polygon? Okay. Now, intuitively, perhaps all of you feel that, okay, yeah, the number of sides can be more for the inner polygon, but the perimeter in the end should actually be smaller for the inner polygon. Okay, so that is, this statement is always true. Yeah. Now, why is it true? Yeah. So is there a simple mathematical proof we can provide that the inner polygon must have a smaller perimeter than the outer polygon? Now, maybe some of you raised your hands and claimed you're physicists. You could perhaps say that, if I were to place a rubber band nicely hugging the outer polygon and suddenly remove the fences that guard the outer polygon, the rubber band is only going to shrink to come and hug the inner polygon. So the rubber band has become smaller, so it must be the case that the inner polygon is smaller than the outer in perimeter. When you finally try to ask, is it true that every part of the rubber band actually shrunk when you go from an outer polygon to inner polygon, it gets a little touchy. Yeah, that, I mean, a proof based on that can eventually be derived, but it is not a totally obvious statement that the inner polygon has a lower perimeter than the outer polygon. So what I want to show you today is a probabilistic proof that the inner polygon actually has a lower perimeter than the outer polygon. So here is the idea. Okay. So let's read this together. So what I'll do is first pick a line at random. Yeah. So you take a line and it can be, so you just rotate it at random uniformly and just place it there. So now you have placed this line and you project the outer polygon onto the line. So you see this little blue band, that is the shadow of the polygon on the line. Is this making sense to everybody? You draw a line, take the polygon and look at its shadow. Yeah, the sun is somewhere here and it casts a shadow, and that shadow is this. And the inner polygon also casts a shadow. Now, since the inner polygon is inside the outer polygon, clearly the shadow of the inner polygon will always be contained in the shadow of the outer polygon. Okay, that is true. Yeah. So good. Now, what is the length of the the yellow shadow and the blue shadow? Now, since the yellow shadow is always contained in the blue shadow, the average value of the yellow shadow will always be less than the average value of the blue shadow. So suppose there are two objects which are being picked at random, and this is always smaller than this. Yeah? Then the expected value, the average value of this will always be less than the average value of this. Okay, so far I have brought you, so it is, this part is always true. Now it turns out that the length of the shadow is always proportional to the perimeter. because no matter which length, the expected length, the average length of the outer shadow, yeah, is proportional to the perimeter of the outer polygon, and the average length of the inner shadow is proportional to the perimeter of the inner polygon. Okay, so suppose proportional means it is, if you look at the average, it is always some constant times the perimeter, and the other shadow is also the same constant times the perimeter. And we have already convinced ourselves that this statement is true. So the perimeter, yeah, so if this quantity is less than this quantity, that means this is less than this because the constant of proportionality is the same. Okay, and the proof ends. Yeah. So the only statement that only thing you need to convince yourself is that when you take a polygon and you project it, the length of the shadow is the same proportionality constant times the perimeter of the original thing. Now, why is that true? So let's look at this example. Yeah. Now, as you go along the perimeter of this polygon, what happens? Yeah. So this is the entire shadow that it casts, but this S1 casts a little shadow X1. Then as you move, it casts a shadow X2. Yeah. Then X3, X4, X5. Now, if you sum these numbers, it is exactly 2 times this length, because you went from the left edge to the right edge once like this. In that case, these shadows, for example, the shadow of S2, S3, and S4, yeah, S2, S3, and S4, their shadows add up to exactly the shadow of the polygon, and these, the bottom chain of the polygon, also adds up to this. So the total shadow is exactly this sum is exactly 2 times this. Okay, this again by first principles. And now we are now left to understanding just each edge. If you take a particular edge and take a random line and just ask what is the expected length of the shadow that it casts on this line, it should be proportional to this line. If you make this line double the length, the shadows will be double the length. Okay? So it will be the same proportionality constant, and that is basically the proof of this statement. I have written it in some sort of formula, but whatever you understood intuitively is enough for me. If you go home and do the integration and come to the constant, you will realize that the constant is actually 2 over pi. Okay? But the important thing is it's a constant. Okay? But the point I was trying to make here is that this is the probabilistic method of proving a statement which doesn't have a probability, that the perimeter of the inner polygon is less than the perimeter of the outer polygon is either true or false. But its truth was established using probabilistic reasoning. Okay? Yeah. And sometimes, even though the problem is static and has no probability, it is useful to imagine a probabilistic experiment which sheds light on the problem. And this method has been very powerful and influential in many areas of mathematics, and this is one such example. So I don't know how much of it you will remember, but in the evening, try to recreate it for yourself, and it will be useful to you later. Okay. So this was the first example. Let me just summarize what we did. The shadow, yeah. So if you take any line and look at its shadow, the shadow doesn't estimate the length of the line correctly, because if the line is sort of perpendicular to this, then its shadow will just be a single point. Shadow doesn't automatically estimate this correctly. Yeah? But if you take a random line and compute on an average what it does, it is what in statistics is called an unbiased estimator of the length of the line, and this idea extends to perimeter as well. So we added randomness to the problem to create some sort of a symmetry, and then the final conclusion was established, and the important point is with certainty. There is nothing like this statement may be true, may not be true, 80% of the time it is true, nothing like that, always true. But we pass through probability to establish it. Okay, sorry, I've probably said more than it is necessary for this audience. So let me move on to the next example. Sorry, so if you didn't understand, let's start again. Okay, it's a completely different example. Yeah. So this example is related to number theory. Yeah, so it's about sum free sets. So let me read the definition for you, and then I will show you some examples here. So a set of integers is sum free if the sum of two elements from the set does not yield an element in the set. Yes? So you cannot get two elements from the set, add them, and produce another element which comes from the same set. Okay? If a set has this property, then it is called sum free. Yeah? You are not able to create an element in the set by summing two elements in the set itself. Okay? So for example, if you look at the set of all, let's say, odd numbers, is this sum free? If you add two odd numbers, what will you get? Even number. Okay, so it will definitely not be in the set. So the set of all odd numbers is sum free. Okay. What about the set of even numbers? Sorry, I didn't start at 0. Yeah. Yeah. So yeah. So look at the set of all even numbers. Is it sum free? I mean, in this example itself, if I added 2 maybe to 4, yeah, I get 6. Yeah, or if you want to be really brutal, you can say I add 2 to itself. Yeah, so here are two numbers, sorry, two numbers, 2 and 2, and I add them and I get 4. Yeah, so the second set is not sum free. Okay, so maybe I should be fancy. I should say, yeah, so this is sum free, this is not sum free. Yeah, these are all squares of numbers here. Yeah, are they sum free? I don't know how many of you remember your trigonometry, and there was always a right angle triangle drawn, and one side was 3, the other side was 4, and the hypotenuse was? So 3 squared equals 5 squared. So that example shows that this is not sum free. What about cube? So are there 3 numbers so that you take the cube of the first number, cube of the second number, add them up, and then you get the cube of the other number? Yeah. So this is one example of what's called Fermat's last theorem, yeah, that such a thing does not exist. Yeah. Okay. So yeah, so this is sum free. This is sum free, and I believe, I don't know, yeah, so here if you add 5 and 12, you get 17. So this is not sum free. Yeah. Yeah, good. Okay. So you understand what a sum free set is? Yeah. Good. What's the theorem? So this is a theorem of Erdős himself. Yes. So you give me any set. Yeah, give me, no matter how complicated your set is, it has n numbers. You can select out of those n numbers about 1/3 of them, which are sum free. Yeah? So the original set may or may not be sum free. You can always keep 1/3 of the elements and then ensure that they are sum free. Now, why such a theorem would even be useful is not clear. I mean, but actually it has deep applications in computer science. Okay? But that's not our concern today. I hope this problem is interesting enough. Like every set of n elements contains inside it 1/3 of the elements which are sum free. Sum free meaning you add 2 of those elements, it will not produce another element in the set. Okay? Now one might try to come up with some algorithms to filter out the desirable elements so that this sum free property is true. it gets complicated. Okay. But Erdős came up with this amazing probabilistic argument which shows that this is true. Okay. So, all right, so we will come to this, but look at this circle. Yeah, I mean, you all understand what this circle is, and you understand that every point on the circle subtends an angle theta at the origin. Yeah, and you understand that I can add 2 points. If I add θ1 and θ2, I get probably a point which is at an angle θ1 plus θ2. Is this clear? Yeah, and the total angle is 360 degrees. Very good. Yeah. Now, there is something funny about this region. Ignore the edges. If you take any 2 points here, yeah, there is θ1 and θ2, yes, and you add them, will you still be in the blue region? If you add 2 things which are at this edge, 120 degrees, they land up here. If both the points are to the right of 120 degrees, then they will add up beyond 120 degrees. Yeah? And if you take this angle and add it to itself twice, where do you land up? If you add 240 with 240, you come to 120. But if you're just to this side of 120, then if you add those 2 numbers, it won't quite reach, sorry, 2 of this side of 240, it won't quite reach the 120 degree line. So I'd like you to convince yourself that this blue region that I have is actually sum free. But this is sum free in the range 0 to 360 or 0 to 359, whatever you want to think about it. Okay? But that was not our problem. Our problem was somebody has given us a fixed set, and they want us to derive from it 1/3 of its elements, which are sum free. Okay? But somehow Erdős thought about this, okay, while thinking about that. Okay? Now, of course, this needs mathematics and also, you know, and talent. Yeah. Okay. But here is what he did. He said, let me pick an angle omega uniformly at random from this. Okay? And then take this element bi, yeah, and so bi is one of these elements, and place it at the point omega times bi. So let me draw it. So suppose I picked up this angle omega, and then my element was 3. So I will take omega, then 2 omega, 3 omega, and this will be my point omega 1. Yeah? If b1 was 3, yeah? b1 was 7, well, probably omega, 2 omega, 3 omega, 4 omega, 5 omega, 6 omega, 7 omega, something like that. If omega was 1000, well, you will probably go around this circle many times and eventually settle somewhere. Okay? Now, so you pick an omega at random and scale every bi so that it falls somewhere. How? You multiply omega, the omega that you have chosen, by bi and place it at that point, remembering to go around the circle consistently. Okay? Now, the point is that if 2 numbers, yeah, let's say b5 and b7, add up to b20, then the place where the angle where b5 landed, that is omega 5, the place where b7 landed, omega 7, those 2 angles will also add up to omega 20. Okay? So if I could somehow convince you that when I do this random process, at least 1/3 of the elements will get placed in this blue region, then those elements originally must have been sum free. Because if they were not sum free, they could not all have landed up in this same blue region. Okay, so that's the only thing. If I take an element and do this mapping by using a random omega, what do you think happens? If you take an element and you map it by hitting it with omega, it's going to fall anywhere in the circle with uniform distribution. Yes? If you pick an angle uniformly in the circle and scale it by 90 or by any integer, it's going to be still, it might wrap around the circle many times, but it will still fall uniformly in the circle anywhere. Now, each of those elements is uniformly falling on the circle. How many of them do you think will fall in this region? 1/3. End of proof. On average, 1/3 of the elements will fall in the blue region. That means the number of elements that fall in the blue region is at least 1/3 n. That means there is a magic choice of omega. There must be a choice of omega where at least 1/3 of the elements fall in that region. If the average age of a class is, I don't know, 23, then there must be at least one person in the class who has age 23. Yeah? If on average 1/3 of the elements fall in this region by choosing omega at random, there must be at least one choice of omega which makes 1/3 of the elements fall here. Those elements, when taken back to the set, and if we look at them, they must be sum free because their angles are sum free. Okay? Sorry, I don't want to belabor this point again. I did some calculation, but I think for this audience it is superfluous. Good. So, yeah, you already said, many of you said 1/3 of the elements will fall inside this. A omega was the set of elements that fall in this region. Okay? Yeah, good. So let me summarize again. So a fact was established with certainty using a probabilistic experiment. The statement is every set has 1/3 of its elements somewhere which are sum free. No probability. The statement didn't say if you pick these elements at random, then they will be sum free or something like that. There was no randomness involved in the statement. Nevertheless, we proved it by this device of probability. Okay? Yeah. Now, this particular problem, yeah, so 1/3 comes out of this argument. Could it be that a cleverer argument gives more than 1/3? Yeah? And this is a topic of research even today. Yeah? But what is known is that you cannot get much better than 1/3. So there are sets of n elements where you can definitely get 0.33 n, 1/3 n, which are sum free. But if you try 0.4 n, yeah, you will not be able to get. Anything better than 0.33 n, there are awkward sets where if you try to get more than 0.33 n, 1/3 n, then you will start producing triples where a plus b is equal to c. Okay? So this was proved only recently, 2014. So one could ask if 1/3 is the correct answer. Okay? Yeah? Is it that even 1/3 n plus 1 is not possible? Yeah? And actually, a famous mathematician, Bomberi, showed that 1/3 n plus 1 or 1/3 n plus 2 is not possible. But actually, it turns out, and this was again a graduate student in England who recently established that there are sets of, so every set, every set has slightly more than 1/3 elements which can be filtered out. But that 1/3 elements, the extra that you get over n is a very tiny amount, log n. Okay? Log n is a very small number usually. Log n is, yeah, I mean, there are rumors that it grows to infinity, but yeah. Yeah. So it's very, very, very small. Yeah, very small. Yeah. Yeah. Okay, good. So do I have time for another example? Yeah. So are you okay? Question? Yeah, please. Yeah, just a little louder. Sorry, so how does he establish this statement you are saying? Yeah, so here it's not a question of probability. So this requires what this is an important theorem in an area called additive combinatorics. So where you prove theorems by showing that no matter which set you take, if it is dense enough, it contains inside it random looking objects, objects that have properties which are random like. This is a very modern area of mathematics where you say that out of determinism you get randomness. Okay? I don't know enough about this area, but that is the rough spirit of how it is proved. It does not come out of anything that I have told you. Okay? Yeah, it wouldn't have taken till 2025 to prove it if it was that simple. Yeah. So there is a fixed constant, let's say 0.00001, so that any set which is large enough will have not just 1/3 n, but now it could be that n is so small that that log n is actually, you know, a very small number. Yeah, then this just says 1 more than 1/3 n. But the point is that as your n becomes larger and larger, the amount that you get more than 1/3 n, yeah, the amount that you get more than 1/3 n is not 1 or 2, but this excess that you get, the bonus that you get, also grows to infinity. That is why it is you know, charming for number theorists. Question? Sorry? No, no. Greater than, that is less than or equal to 1/3 n was, sorry. Yeah, so greater than or equal to 1/3 n was already proved by Erdős. And this student is able to improve Erdős's theorem and say that Erdős can only prove 1/3 n, I can prove 1/3 n plus c times log n. Yeah? Yes. So this says that yes, you can, this says that you can prove slightly better than 1/3 n. This says you cannot prove much better than 1/3 n. Okay? Only slightly better. Yeah? So if this, let's say 1/3 is 0.33 for today, 0.35 n, yeah, you cannot prove such a theorem. Okay? That's what this says. Yeah? But this says you can get slightly more than 1/3 n, not just 1/3 n plus 1 or 1/3 n plus 2. You can really get substantially more than 1/3 n. Okay? But not very much more. Is that okay? Are the statements clear? This, I think this little o of n is not something that I defined. Little o of n is a number that goes to 0. Yeah, sorry. When divided by n goes to 0. So square root n, a number like square root n is little o of n. It's not the same order as n. But 0.5 n is not little o of n because it, you know, even if you divide by n, you still get 0.5. Yeah? If you take log n is little o of n. Okay? So they show 1/3 n plus some number which is slightly less than n, let's say n over log n. Yeah? Yeah. Something like that. All right, is that okay? Yeah. So this, yes, so I'm going to assume that I can continue. Yeah. 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 So finally, so problem in computer science, a computer algorithm. So randomness so far was used as a device for establishing mathematical theorems with certainty, but by casting them as probabilistic statements. Or sometimes it looked some completely bizarre to bring in probability, but nevertheless it was effective. Here's a problem. So I don't know, many of you, we have all been tortured with this definition in high school. Yeah? So operation is commutative, associative, distributive, yeah, all these scary terms. So I'm sorry, we'll have to do it once more. Yeah. Yeah. So yeah. So when do we say that an operation is one? Yeah. So what's an operation? An operation between two, yeah. So there is a set and there is a binary operation. Binary operation means it takes two elements, combines them using this operation, and produces an element again in the set. So here, how do you describe an operation? You have to give me the table. So A, let me call it multiplication. Yeah. So let me call it composition. So when A is composed with A, what do I get? A itself. If I compose C with D, what do I get? If I compose C with D, yeah, C star D. According to this table, what is C star D? C, somebody says. So what should I do? I should look at the row of C, because the first element here was C, and the column of D, and look at the answer here, and that says C. Yeah, okay. So somebody has given us an associative operation using this table. Yeah, if the set has n elements, how big is this table? If there are n rows and n columns, how many elements are there in the table? N squared. Thank you. Good. So there are n squared elements in this table. Okay, good. And when do we say that this is associative? Here's the definition. If you take an element from the table, take 3 elements in the table, multiply these 2 first, and then multiply it with this in the same order. Yeah, yeah. AI, AJ, AK. First multiply AJ and AK, and then multiply them with AI on the left. This gives you some answer. On the other hand, you put the brackets this way. That's what I've done here, and multiply it with AK. You might get a different answer. But if you always get the same answer, then the operation is called associative. Okay, so all this you know. Yeah. Now I give you this table, and I ask you, is this associative? Okay. Now, when would it not be associative? If I can find 3 elements, AI, AJ, AK, so that if I multiply them in this fashion, and I multiply them in this fashion, I don't get equality. Something goes wrong. Then I say that the table is not associative. For every triple of elements, if it works correctly, then I call it associative. Now, a computer scientist has been given this table, yeah, such a table, and they have to answer the question, is it associative or not? At any time, they can take 2 of the elements, go refer to the element in the corresponding row and column in the table, and do their analysis. How many times do they have to look into the table? Okay. Now, in this table, it turns out that it is not associative, because if you multiply D times B, well, if you take D times B, sorry, what did I do? D times B is D, yes? And if I multiply D with D, yes, I get B. Whereas if I multiply D with itself here, sorry, what did I do? I should have done D times B first, yeah. If I multiply D with D, I get B, and B times B is B. So the left-hand side and the right-hand side are not equal. I'll let you check. I don't even know if what I said was correct. Okay, but yeah. Okay. So if I have to pick 3 elements, I pick an element, how many choices? N. Then I pick an element again, N. How many? Again. What is the number of choices? If I have to pick 3 elements from a set of size N, N cubed choices. Okay? So I could try every N cubed possibility, and in the end come up with the answer. But that would take how much time? N cubed time. Can we do this faster? Faster than N cubed. After all, the data has size N squared. Why should I spend N cubed time to determine whether it is associative or not? Yeah. And it turns out that you can do it in N squared if you use a randomized method. And in this case, the method will have some very small probability of error. Yeah? And the method goes like this. Yeah. So what you do, yeah, so this is a method due to Rajagopalan and Shulman. Yeah. So here is what we do. You pick weights W1, W2, Wn. So to each of these elements in your set, you associate a weight. There's a question. Yeah. Sorry, previous slide. Yeah. Both are equal. Oh, I see. First one is equal, huh? So
yeah, first one is equal, B,
D,
second is okay.
Okay, so this is a correct example, and so this is associative, this is not associative. Yeah, okay, sorry, I probably just copy and pasted, did something while making the slides. Question?
Somebody gave you a table. Yeah? No. In the course of their mathematics, they wanted to check whether this particular operation is associative or not. So they wanted a computer to check it for them. Yeah? So sometimes you do, so many of you do matrix multiplication. Yeah? Now multiplication, okay, we have been told is associative. Sorry? Yeah. So, but is matrix multiplication also associative? It turns out it is. Okay. So sometimes you might come up with certain operations in the middle of your mathematics where you take two elements, combine them, it produces a third element, and you want to know whether the combination process brackets are important or brackets are not important. Okay. Usually when you write multiplication for numbers, brackets is not important. Okay. Because whichever way you multiply them, the answer is always the same. The question is, do we need to put brackets for some other operation? Okay. So somebody gives you a 1000 by 1000 matrix with various elements, and they ask, is this associative operation or not? How much time do you need to spend to check this? How many for loops will you write? For I equals 1 to n, for j equals 1 to n, for k equals 1 to n, then it becomes an n-cubed algorithm. Can you do it with just 2 for loops or something cleverer? Okay? And the method is the following, and it uses randomness. So what do you do? To each of these elements, you assign a number in the range 0 to 5, and build this sum, a weighted sum of elements. Yeah, you cannot really add elements. The only things you can do to elements are multiplication, but just pretend a weighted sum, and you write it as a sum, as a polynomial if you wish. Yeah? So to each of the abstract elements of the set, you assign a number in the range 0 to 5. And then you take this sum, and this sum, and multiply them as polynomials. So here, when you want to multiply A5 with A7, what will you do? You'll go to this table, see where A5 is, where A7 is, and pick up the answer. But if you have to multiply their weights, say 3 and 2, what is 3 times 2? 6. But we are in the world of 0 to 5, so we reduce everything mod 5. So what is 6? No. When you take 6 and divide it by 5, what is the remainder you get? 1. So you should think of 0 to 5 in a circle. So 6 is the same as 1, 7 is the same as 2, and minus 1 is the same as? Yeah, sorry, I made a mistake. 0 to 5, so 6 is 0, yeah, 7 is 1, yeah, and 5 itself is minus 1, because if you add 1 to 5, you get 0, yeah, okay. So using those rules, you do this addition, you do this multiplication on this side and do this multiplication on this side. Now when you have two polynomials with n terms and you want to multiply them, how much effort does it take? If you have n terms in a polynomial, n terms in a polynomial, how much effort does it take to multiply them? You will take, how do you open brackets? Yeah? If you have a bracket like this with n terms here and a bracket like this with n terms here, and you've been asked to multiply, you'll take the first element here, multiply it with the first with the second, this is called distributive law. Yeah, so you will multiply and add them up. So if you have two polynomials, two such expressions with n terms, how much effort will it take to multiply them? N times n squared. So you perform this multiplication in n squared steps. With the result, you perform this multiplication with n squared steps, maybe 4n squared steps, 5n squared steps. This whole thing will be done, and you check the answer. And a little calculation shows that if it is associative, you will always figure out that the two sides give the same answer. But if it is not associative, if even one place there is a mistake, this computation will catch it with probability half. 50% of the time you will catch it. If you want to catch it 90% of the time, repeat the experiment with random weights 10 times and you'll catch it. The total amount of effort is only n squared. So the original naive way of doing this computation required us n cubes amounts of effort, but there is this randomized process which requires only n squared amounts of effort. Okay? So I don't want to tell you the calculation. It's not very hard, and hopefully these slides will be available to you somehow on some website, so you can check it for yourself. So yeah, so there are many other things I could have told you about probability and computation, randomized algorithms, of which this last example was a special case, pseudo-randomness, average case analysis of algorithms, quantum algorithms, and information. All these have probability in them and are deeply important in mathematics and computer science. You are all young people, and there is this final little passage that was written in 1989, and I would just like to read it out to you. Yeah? So why have we realized that randomness can be used in computation? That is, why now? And here is my explanation. I believe the main reason to be that we have become increasingly comfortable in living with uncertainty. The uncertainty, I mean, of human survival. Okay, so I'm going from my little mathematics to very far now. Yeah. Only after having achieved a good chance of nuclear and ecological disaster could, for instance, the notion of a proof that has a chance of being false become so readily acceptable. It is true, to be fair, that nowadays the individual experiences a longer and safer life, but humanity as a whole stands at greater risk. Science is primarily a social enterprise. It is this common risk that has paved the way to accepting previously too daring scientific concepts. Exciting times indeed, scientifically and otherwise. That was 1989. Yeah, I don't know if the chances of human survival are better now than it was then, but all that depends on you. Okay, so thank you very much. That's all I had to say.
Thank you, Jaikumar. So any questions? Or yeah, the one there.
Hello. Nice talk, sir. I had a doubt regarding the first example,
Yeah,
the expectation of the shadows.
yes, yes, very good.
So can we apply this to circle?
Yes, very good.
So
Yeah.
when I applied to a circle of diameter d,
Yes,
I got the shadow as d, the expectation value
if
of
it's always d, yeah.
yeah. But the perimeter is pi d.
Pi d, yes.
So the proportionality constant, you
Yeah,
told
so
it was
this was a proportional for a circle, so this will only for half the sorry. So when you apply it to a circle, yes, so the shadow, yeah, is yeah, so this S1 you should think of as only the upper part, yeah. So it is 2 over, so I think, yeah, so if you,
I just calculated it for a square, and
no, it is, yeah, so the question is whether this 2 is there or not.
no, I calculated it for a square and I got a totally different.
No, you should do it
Constant.
for a random line. You probably calculated for one line. So let's do it for a circle. 1 second, yeah? Let's do it for a circle. So here is a circle, and suppose its diameter is d.
Yes.
Yes. So so here I'm only talking about a line versus its shadow. Yeah. But you're talking about a circle and a line, and you're asking what is the relationship between the shadow that it produces here and the circumference.
Yes.
Yes. So let us call the shadow S and the circumference C.
Yes.
Yes. So in this case, if this is D, so C was pi times S.
Yes.
C equals pi times S. Yeah.
Yes.
But Now if you took, instead of this line, a different line and took the shadow, it will be the same. Yeah?
Yes.
So in the case of the circle, we have this pleasant situation where the shadow is always of the same length, and in that case, the proportionality constant comes out to be pi. The claim is for every convex polygon, the proportionality constant will always be pi. Okay? Now you said, what about a square? Yeah?
Yes.
And in this case, suppose this was just d over 4, sorry, whatever. Yeah.
D by root 2.
What would you like the length to be called?
D by root 2. I took the diagonal as D.
You can take the diagonal as d, yes, but I'm talking about the perimeter. But I'm okay with, yeah. So what would you like this to be called? The vertical line to be called?
The side.
Yeah.
D by
Okay.
root.
Let me call it d. Yeah.
Okay.
All right.
Okay.
Now, what is the perimeter of this square?
4D.
4d. If I took the line like this, I would get the shadow of d. If I took it exactly as 45 degrees, I would get it. If I took exactly at 45 degrees,
Root 2D.
root 2d. Yeah. So, and that you can imagine is the longest. So it's a number between d and root d.
Yes.
And depending on this angle theta, it will vary. My question is, what is it on average? And average, the circumference, that is the perimeter, will be pi times the average shadow that it casts. Okay?
For me, I got root 2 pi. I might have done some mistake. I'll talk
Yeah,
afterwards.
it's always the same, no matter which. And the calculation is here, so it's not a very deep fact. The calculation is on this page, but I didn't bother you with it. But we can discuss it afterwards. Yeah. Thank you very much. Yeah. There's other questions also. Yeah, we can do.
There's one more at that side,
Yeah. Yes, sir.
behind.
Thank you, sir, for the good speech. Sir, I had a question in the next example where you said that a particular set or 1/3 of a set should lie in a particular area that is between 120 to 240.
Yes.
Sir, if I take a set of, to say so for an example, a set of single digit odd prime numbers,
Yes.
that is 3, 5, 7.
Yes.
And if I take omega as 95,
Yes.
neither of them lie between that area that is 120 to 240.
Agreed. What did I say? Pick omega uniformly at random. So pick an angle at random and then ask on an average how many elements go there. Don't show me one omega which doesn't work. My claim is that if you pick the omega at random and compute it on average how many of them are falling there, that will be 1/3. Okay, so what you observed does not contradict what I had claimed. What you should have done is try to ask, if I pick an omega at random, yeah, in the range 0 to 360 degrees, yeah, what is, on average, how many elements fall in the blue region? Okay, that was the claim. Yeah, thank you. Yeah, these are all questions about averages, yeah, not about a particular value of omega. Yeah, question,
Okay,
Pete. Yeah.
Yeah.
Yeah, please. Oh,
The rubber band proof that
Yeah.
you originally mentioned
Yeah.
about convex polygon.
Yeah.
It appears to me that even if you take a non-convex polygon and an embedded non-convex polygon, the rubber band argument would tell us that the perimeter of the embedded non-convex would still be less.
No, it depends on how you write that. So if you had a big polygon like this, and inside that, yeah, and now my rubber band is green, okay? So initially I have this rubber band here. That means I place some pins on this drawing board and stretch my rubber band and left it, and it nicely sits here, okay? Then I pulled out those pins. The trouble is, because of this crazy behavior of physics and physicists, the rubber band will not hug the inner polygon. Yeah, so the length of the rubber band is not a fair description of the perimeter of the polygon. That's why we stick to convex polygons. In the case of convex polygons, of course, the inner, when it shrinks, it will nicely hug the inner polygon. But the point is it true that every piece has actually shrunk in the process? I can create examples where actually in the process of going and settling down into the inner polygon, momentarily some parts actually stretch. If it was uniformly only shrinking, then this argument would be a valid logical argument. The trouble is the physics that I sort of tried to deploy sometimes even increases the length of the polygon as it goes in, okay? Increases the length of the rubber band or stretches the rubber band more than it was stretched before. Then I need to say that the stretch here was compensated by the contraction somewhere else, and then I go chasing physics ideas which I don't understand. Okay.
The last question I had was
Yeah.
wherever you are using uniform probability,
Yes.
it appears to be, it is due to symmetry the result is forming.
Yeah, many of the
Is there a symmetry argument?
That is true. Many of these arguments are because of symmetry, but not all applications of the probabilistic method are because of symmetry. See, originally when this 1/3 of the numbers are sum free, the original numbers were completely crazy. The symmetry was invented by Erdős to place them on the circle. Yeah, who would have thought to think of the circle when presented with a set of numbers? Okay. But there was some way to cast that problem into this symmetry. I agree that the final probabilistic argument was because of symmetry. That is, whether the line is placed like this or placed like this, its average shadow on a random line will be the same because of the symmetry of the underlying space. Questions?
So maybe we should.
Yeah, thank you very much for listening.
Yeah, so Jaikumar will be around for the rest of the day, so you could ask more questions in the breaks.
Yeah.
Yeah, sorry, I have to
Yeah.
hand over. So,
Okay, thanks. So, yeah, okay, so I have many pens here. So, yeah, so, yeah, so this is the next speaker's pen.
Yes.
Yeah.
So in fact, the pen belongs to the next speaker, I think.
Yeah, so you keep yours and then.
The change in the order of talks. So Professor Shabnam Miani will speak now, and I request Madhavan to continue to chair this session. Your pen is there, but your talk is not there. Professor Hema Samanathan's talk will be tomorrow, at the time that this is supposed to be. And after this session, maybe we will have another photo session here on the stage, if that didn't come out well. We'll see.
quit. No, you should just say quit. You should. You do it. So our next speaker, as Professor Suri said, is Dr. Shabnam Miani from IISER Trivandrum, local faculty member. And it's a topic I know nothing about, so I'm looking forward to it. Thank you.
So, a very good afternoon to one and all. And thank you all for coming to IISER Thiruvananthapuram. It's happy to host you all here. And I hope I'm audible and clear? Yes. Okay. So, So starting from a wonderful talk that was given previously on randomness and things, which is very much a part of what we do, especially in astronomy, dealing with a lot of data and things. We have most of our algorithms based fundamentally on that. And so in my talk, I'll be talking about something in the frontiers in high energy astrophysics. But basically, I want to take you along in a journey which is a journey through space and time. So when we do astronomy and astrophysics, it's always a journey through space and time. Now I want to ask you, what is that, the most, I would say the most simplest thing, or that is very much in your daily life experience, that you are very familiar with a quantity of measure that you deal with space and time? Can you tell? That connects space and time together. Can you think of? Is there in your very daily experience? Huh? Travel. Yes. But how do you, travel, when you say it's more qualitative, like you say, okay, I'm traveling, but how do you make it more scientific, methodical? Speed, right? Speed is that one fundamental quantity that is there in your everyday life experience, which simply connects these two very fundamental parts of physics, that is space and time. And that begins where our journey through space and time in whatever that you look gives the insight into it is basically from there. Okay? Yeah. So as I said, the speed is that quantity which is we are all familiar with what speed is. It is distance by time, where distance is that as a measurement in space which gives you an idea of space, and time, of course, it gives you what you think of. Now, as I said, as this connects through this, in astronomy that gives you a very good insight into this quantity is basically given by Einstein, who in his special theory of relativity said that the postulate of that is basically that the speed of light is a constant. So that means, so it has a very direct implication. That means you cannot have any speed, or you cannot have infinite speed or anything. The speed is finite in its nature, that there is some maximum value that you can attain. So what does it basically tell us? If you look out into space or look out into the sky, what does it basically tell us? For example, if there is sun, we are looking up, we are seeing sun, yes, right? So what it basically means is that when the light travels from the sun and reaches us, the telescope, we are basically seeing the light basically takes around 8.3 minutes to reach us. That is, you know how the sun was 8.3 minutes ago, even though you make the measurement now. You do not know how the sun is now. You only know the sun 8.3 minutes ago. So if I ask you, is the sun there in the sky now? Your answer should be, I don't know. Right? I don't know whether the sun is there now or not. Okay, after 8.3 minutes, I will know whether it was there 8.3 minutes ago or not. Okay, so this concept of time and space, there's that information, it's not instantaneous. There is a gap in time. And this is how, when I say when you study astronomy, we kind of travel in space and time. Okay. So this is one of the deepest images that is made by Hubble Space Telescope about one patch of our sky. And you can see most of each dot that you basically see here is a galaxy. Okay, it's not stars we are talking about, most of it is a galaxy. And you see that all of these galaxies, are they now there in the sky? Definitely I have no idea, it's not there. They have traveled millions and millions of years to reach us. So we know how they were millions of years or billions of years ago. We do not know whether they are there now or not. So we I always say we live under the dome of past. When you look up at the sky, you see the sky, how beautiful it is, is this many billions of years ago. You live under the history of the dome of past. It's not now. You do not know anything that is now, right? Okay. So therefore, we are in a way a study of history of space and time when you do astronomy and astrophysics. So can you tell me what is the farthest object that you can see in the sky with the naked eye? When I'm telling that, it is not in cities or there we might not be able to see even the closest of stars that you can see. And I'm talking about if let's imagine if you were in a very with less of light pollution and so, and if you look up, do you have an idea of what is the farthest object that you can see in the sky with naked eye? No. You can see something even farthest. Yes, so it is the Andromeda galaxy that you can actually see is the farthest that you can see with our naked eye. So now, see, so in this universe right now, we know that in the Milky Way galaxy, there is a star like Sun. So Milky Way galaxy is a spiral galaxy with millions of stars in it, and then Sun is one of the average stars. It's not anything very spectacular about it. And there is a planet around it where it is hosting life, right? So it is not, I would say, very extraordinary anything about this, but we have still not found any other life, which is one of the major domains of research in part of astronomy and astrophysics. Also, people look for extraterrestrial, where there can be, where you use physics, chemistry, biology, everything to put forth to understand what are the mechanisms or, the environment that you need to host life. Okay. So let's imagine that in the Andromeda galaxy, maybe they also have one star which may be hosting life, and let's say they are also somebody like us who is inquisitive about what to know, what is there outside. See, if they also look at, at us, let's say, they plan to look at us, what they will see? No, not that. So you see, Andromeda galaxy is 2.5 million light years away from us. So it would be around 2.5 million light years ago how we were. So in the history of life, they will be seeing humans, not that ago as dinosaurs, they will not be seeing that, they will be still seeing humans, but it will be in a Stone Age thing, okay. So they will not be seeing any kind of what we are thinking of ourselves, how technologically advanced we were, or like, this light and billions of or buildings and other things. This is not what they are going to see. They will be seeing us as humans, very prehistoric, in the Stone Age, and this is how they would be seeing. So you can understand how much is the gap of generational gap. We talk about one generation to another maybe, but in astronomically we have too much of gap of information between each other if we are trying to communicate. Okay. So with this idea of understanding that, looking at objects, we are looking not just in very far away objects, we are also looking back in time. So this understanding has to be there in the back of our head when we study astronomy and astrophysics. That's why I began with this. So with this, I will kind of introduce you to the very high energy part of the universe. So the stars and other things is gently being studied, but we also will look at some of the phenomena that we know in very high energy universe. So in that, some of the phenomena that is quite maybe familiar to you. So one is the solar flares that you might sometimes hear nowadays in the newspapers and others, that because the solar flare and studying the solar weather that we call these days, because we want to know, because we have a number of satellites up in the orbits, which gets very much disturbed by these very high ejections of masses, which contains a lot of charged particles and others, which kind of disrupts most of our satellite systems. So therefore, it is kind of one of the main studies in solar physics is to understand how these ejections happen, when it can happen. So if we can understand the fundamental phenomena, we may be able to predict it, and we can have certain setups that can help protect us from many of these things. So this is one of the closest of us that gives it. And the other is the supernova that might be also very popular and familiar among students. When stars basically die, some of the very massive stars die in a very explosive fashion, emitting a lot of energy during that process. And the others is basically kind of X-ray binary system. So that is, most of the stars that we have are in binary forms, and if one of the stars actually die and form very compact objects, it is possible that they can start eating up the star which is in its bound, and it creates very strong emissions like jets and X-rays and others. So they are referred to as X-ray binary systems. And you also have something called as tidal disruption events, which you can largely see when you look closer to the center of galaxies. So that is, most of our many of the galaxies whose centers are basically hosted by very huge black holes, which are extremely massive black holes. That is, we are talking about 10 to the power 8 times or 10 to the power 9 times of the solar masses. So that heavier black holes are there. So when the stars orbit and sometimes they come very close, they can just because of its gravitational power disrupt the star. So that also produces a huge flash of energy that is produced in. So that is what is referred to as tidal disruption events. And then there are also galaxies whose these center of black holes who are actively very energetic, who kind of accretes matter and then produces huge jets, which are also very bright in all the wavelengths. So and also you see it in X-rays and gamma rays and so on and so. So these are all as you can see electromagnetically kind of very dominant. You can see them in all the wavelengths that you see and so. But apart from that, when you say high energy astrophysics, we also deal with objects which may not be like very extremely observant in electromagnetics, but which are actually very massive. So if you have the famous equation of Einstein, E is equal to mc square. So this E being very high is what we are talking about, which can also be in terms of mass. So that is very, very massive objects. When we deal with their dynamics, we are also dealing in high energy astrophysics. We are largely dealing with those quantities itself. So in that perspective, we have like binary black hole mergers, which are also comes under the domain of high energy astrophysics, and also the merger of binary neutron stars, which also creates a huge powerful jets, as well as it has gravitational waves that are produced and detected. And also they sometimes hypernova is like something more energetic than a typical supernova is what is referred to as a hypernova, and they also kind of produce huge energy releases. So they also kind of compose in this domain of high energy astrophysics. So now when you say high energy astrophysics, so because majority of our astronomical observations are still taken in electromagnetic spectrum. So we take it. So you can imagine that historically when we look, people have been very much only looking at the visible band, that we can see that the whole electromagnetic spectrum, when you look at it, it's a very small band in the region, that whole electromagnetic spectrum that we have been looking. That is, I am telling, when you are looking up at the sky also, what you see is only within that limited band. But now the astronomy stands at this point where you span the observations across the entire electromagnetic spectrum, starting from radios till hard X-rays, you have observations. Okay. So so in radios, I hope you are aware, like, because most of the radio part of it can easily travel through the atmosphere and reach the Earth's surface. So you can have your telescopes, most of it, on the surface of the Earth itself. As part of the world astronomy, GMRT, the Giant Meter Radio Telescope that you have in Pune, is one of the major observatories across the world in astronomy. And You have for infrared and others, as you move up, there are some absorptions to some certain depth it can happen. So there are certain facilities that have where you have certain, where observatories they can take up to certain height and they make observations and they come down. So those kind of facilities are there. And then optical, which is well aware, all of us know a large number of telescopes are there on ground. It is there. But as we go into the ultraviolet, X-rays, gamma rays and see, you can see that the transmissibility which is here shown by this vertical arrows, you can see that it kind of goes only to a certain height on the atmosphere and it does not reach the surface of the earth. So this is one of the reasons, like studying high energy part of the universe or whatever the astronomical objects is, we largely have to depend upon equipments or other things which have to be flown into space, which has to come out of the Earth's atmosphere to make it. So in a way, in a budget person, it's a very expensive task where you need to go to space for it. But it is very interesting that, so in I do not know how many of you are aware. So when you go to tera electron volt to penta electron volt of energies, we do not go to space anymore. We come back to Earth and you do the observations on Earth itself. Okay? So largely it is based on fundamental science, the fundamental part of physics or science that is involved in astronomy is what? Can you think about it? Fundamentally, what should we know to do anything with astronomy? We want to design an equipment, okay, how do I want to design that equipment to make an observation? What is the fundamental thing that we want to know? Yeah, so wavelength is, you are talking about what part of the spectrum you want to look at, right? But knowing that, what is going to help you? No, I'm asking, you are talking about just something before that. Just before that, what else is fundamentally you have to know? It is based on that thing, you kind of design, you want to know, okay, what wavelength, then, so what you fundamentally want to know is how light interacts with matter. So, because when you say detection or an absorption means, you are collecting the light, that means light has to fall on something, has to get absorbed by something, there have to be some interaction with matter. That interaction is what you are measuring, right? So you want to know how light will interact with matter, it is then only you can make. So that is why if you look at the history of, like when you want to teach astrophysics in a class, you have to go through almost the fundamental of all the physics, because first you have to understand what is matter, you want to know where electron is, how the electron is placed, how it is, and then you want to know what is light, what is fundamentally light is, and then you want to put together how they will interact with each other. Then only you can make a measurement of things saying that, okay, now I want to understand how the light will interact with matter, and thereby you find out, okay, these wavelengths, we cannot use the same technique of observation from radios to X-rays, because they will not interact the same way. Okay. So that is why, so if you look at, if you come to higher energies part, they mostly scatter, so you use Compton scattering techniques. So if you remember at lower energies, you have absorptions, where the photons will largely get absorbed, that is where you have excitations, de-excitations and those kind of processes. But otherwise, when you come to moderate energies, you have scattering processes, you look at Compton scattering. Now when you come to very high energies, photons in the presence of matter will pair produce. So when you go to very high energies, why we are able to have it on Earth is because when the photons come in the atmosphere, they would pair produce and they will give you a shower of, you have electron-positron pairs will be created. Now these will be traveling in the speed which is greater than the speed of light in the medium. So this will create what we call as a blue flash of light, which is called as Cherenkov light. So what they look for is Cherenkov light. from the Cherenkov light that you can observe from the earth on just from the surface of the earth, they kind of rebuild. They detect the shower and they rebuild and they find out from where part of the sky, and you can get a total measurement of energies. So this is the kind of technique, and we should be proud India has one of the these telescopes which is called MACE, which is placed in Ladakh, in Handley in Ladakh, where we are one of the part of the larger high energy observations techniques where we used for detections here. So now what is the use? So nowadays we call something called as multi-wavelength astronomy. What do you mean by that? That idea is basically you want to observe one object across multiple wavelengths. That is, you can observe it. For example, here I have taken the example is of Crab Nebula. So Crab Nebula is a nebula that is created due to a supernova that had happened close to 1000 years ago. Okay. So now you can observe this using various telescopes which in various wavelengths. For example, in radios when you see it, it would look something like this. So don't look at the color is just given to tell you the intensity of how strong radios is. Okay. So it's not that there is color for radios, that is not what it basically means. Okay. So you can see something that is more hazy, there is some diffused emission coming from there, from sender part there is some stronger radio emissions that you can basically see. Now as you move into infrared, so this is from Spitzer Space Telescopes, you can see there is more, but it is more diffused, but you can see more intense white lights are coming from the sender regions and so. And as you move into optical, this is one of the most popular images that you might see on internet, where you can see you are able to see some structures, filaments, more details that you can see from the Hubble, right. Now when you look at it in ultraviolet, again it is more diffused in the other parts, but you can see that the center part is getting very, very prominent in this thing. And then when you go into X-rays, you can see that, can you see, so this region that the center there is a very sharp dot and you can see something very diffusive like jets or something. There is very strong kind of a disc-like features that are coming around it. Okay. Now when you go into gamma rays, which is observed by this, you can see what it is seeing is the very core region of that nebula, which is well inside the nebula. If you see in optical, you cannot see what is that behind that nebula. The center, what you see is basically what is now we know as a pulsar. So there is a pulsar, that's a fast rotating neutron star. So when the star exploded, what it left as a remnant is a very compact object like a neutron star, and it is fastly rotating. That pulsar is now visible to you. So what is, because these depending on the wavelengths, so that is you can have, when it is gamma rays, they can travel from as an information, as we looked at transmissibility, you can look more deeper into that object. So keeping all these informations together that you can collect, whether it is from timing and others, you are able to create. So when you look at sky, one thing you have to understand is the sky is like a screen. What you see is everything projected onto that screen. Okay. So when you look at something, you see something that is more plain, but the information of depth, and this in an astronomy you have to get it through various means. Okay. So this is one of the ways, by looking at its spectra, or that is information on wavelengths basis, you can create a 3D understanding of that object, how it is placed and what is the content present inside it. So this is why people are very much nowadays interested in using multi-wavelength information to study astronomical objects. So with this, I will come to something that I work on and which I feel is also interesting in the domain as of multi-messenger astronomy these days. That is something called as a gamma ray burst. So it is, as the name suggests, it is a transient phenomena. It just happens and goes. So on average, we are detecting one event per day. So as we are sitting here, there might be one event or more than that happening in that, and these are mostly detected by space telescopes. So what you are seeing here is a sky that is observed in gamma rays, and the bright region you are seeing at the center is basically the gamma rays coming from our Milky Way galaxy. Now when a gamma ray burst happens, it is so bright that it almost outshines the entire gamma ray sky that we are basically seeing for some period of time. And this basically is what we detect as a very sharp rise in number of counts in the detectors, and it goes off. And this is the brightest explosions that is known to occur in the universe. And they come from very, very far away distances in the universe, and they are believed to be a narrow beam of flashes of light. Okay. So, wherever the light is produced, it is that jets are traveling at speeds close to speed of light. So, that is the understanding we have. And apart from that, what is interesting is that there is a glow which extends after that this immediate gamma ray emission. There is a glow which extends over a long period of time, and that is called as the afterglow, and it is observed in all the wavelengths starting from gamma rays till radios we can observe them. And so, the observational history of this is that, so this was actually detected by chance, because these were detected by the military satellites, by Vela military satellites, which were deployed by US to actually keep a surveillance on the then Soviet Union if they were doing any nuclear tests or something. But they detected this gamma rays and they didn't know from where it was coming, because they were not expecting this. So, they kept it declassified for a very long time and then kind of published it once they understood that it had no terrestrial origin. When they understood that, they kind of published it that it was some cosmic origin, but they didn't know. So, it took several years later to have a dedicated missions spent for it to finally find out they came from cosmological origin. So, during that period there were more than hundreds of theories that were put forward, in which one was also that these were messages coming from aliens and so and so. There were a lot of theories that were proposed. It was with this instrument that was sent that in 1991, which was sent, that we started observing them in a more systematic scientific manner. And within its 9 years of observations, we understood every dot here is a GRB. So, every dot that you see is a GRB. So, during its 9 years, it had detected around 2,700 GRBs, and the color is basically the intensity, like how bright it is, that is all. So, you know that it is not coming from our Milky Way, it is not coming from but it is coming from all parts of the sky. And later with the afterglow detection, which again happened 6-7 years later. So, this name of the GRB is the date actually. So, this is 28th of February in 1997, that is what it means. So, you can say 1997 was the first afterglow detection happened, which confirmed that they are coming from extragalactic distances very, very far. So, nowadays we regularly observe it. So, when you have an event, so this is a transient event, it just happens for a few seconds and goes. So, what you have is once they are detected by the satellites, they kind of send a telegram which goes across all the astronomers, and they will have their optical radio telescopes slew towards that region and they start observing it. So, nowadays we also have IceCube neutrino observatories, also gravitational observatories are also linked in. So, it is a huge international effort that has been put forward on a very daily basis. This activity is happening where everybody is involved in making these observations. So, so this GRBs basically, if you can say, each is one of that events. They are very unique, they are non-repeating events, you cannot get to see them again. Once they happens, it is gone, you do not get to see them. So, that makes it very hard to study. Okay. So, and just based on their durations, we have some understanding of their origins. So, one is that they come from very compact binary mergers. So, this was a hypothesis until 2017. And till we had this very famous coincident detection with gravitational waves, which confirmed that they are coming from neutron-neutron star mergers. The other class is very long duration events, which are basically associated with the death of very, very massive stars. We are talking about 100 times more massive than our sun. That is those kind of stars, and this is because we have seen supernova kind of spectra associated with it. So, what is the understanding? So, how is this originating? So, the classical picture that we have is like this. When something like a merger happens, or is it a death of a star, you have a huge ball of fire, that is why it is called fireball, is because that is you have a huge amount of energy produced or put in a very small region, and there is some matter present in it. So, now the radiation pressure is so high that is like an explosion, it pushes the material outwards. So it kind of pushes the matter and it kind of accelerates the jet to very high velocities close to the speed of light. So that is how you get this jet, and the emission that you get from the jet is basically what we refer to as the gamma ray emission. That is what you are seeing as the gamma ray. Then what happens is the jet goes and crashes into the interstellar medium, and that is where you basically produce the afterglow. So this is the basic understanding that we have about this, but you can take any point you ask me, like what is that engine that is powering this, we do not fully understand. How is this jet produced to this very high speeds, it's still a mystery. How do you launch the jet, that is still we do not understand the physics of it. How the plasma physics of the particles, how to produce them to produce this many photons, this very high energy photons, that's something that we do not know. So there is a lot of physics, fundamental physics, which also we do not fully understand. So the interesting is why we study them. Why do we want to study them? So there can be two perspectives to it. So one is like it has a lot of connection to other branches in astrophysics. For example, is that you look at massive stars, how they die, all those kind of physics you can do with it. Interstellar medium, so that's very interesting, is because interstellar medium is one of the toughest parts to observe, because they don't emit light by themselves. So it is very difficult to observe. So now this is like a lab setup, you have done the sodium lamp experiments in your labs, where you pass through the light through a sodium vapor and then you look at the spectral lines. So here it is like this, when a gamma ray burst happens, gamma ray burst is like sending the light through the interstellar medium, which is the gas, and you get to see the properties of this gas, intervening gas. So you can study it. So that is one of the main means of studying interstellar medium. It also tells us about this extragalactic galaxies, what kind of properties these galaxies have, allows you to do that. And also people like to use it for cosmography, is because they want to, these are one of the objects we have observed till as far as redshift of 9. So that is very close to some of the first new stars were formed in the universe. So you can look that deep into the universe. If you basically back in time, you can study them. Allowing us to study about cosmology is one of the reasons that these are also interesting. Now, so this I just said, about the central engines. This is one of the most interesting things. Then people also like to use it to study the history of the universe, because they have been very observed much farther. And now this also has a lot of things to connect to other fundamental parts of it, which I will connect to. So we are all happy that Einstein has given this beautiful theory of GR and special theory of relativity, and we know it. Of course, we have tested, but it is not as if we know that it is not the complete theory yet. Okay, so we still test whether the speed of light is constant or not. And gamma ray bursts are one of the observational objects that we use to test this theory. So that is the Lorentz invariance violations that we kind of do with this. And you can study about strong nuclear reactions, electromagnetic parts of the spectrum, the quantum mechanics, because it comes in all the the physics of emission and other things that you want to study, the relativity, because these objects are traveling with speeds which are very close to speed of light, and gravity, because we have to look at black holes and or whether you look at very compact objects, so how the jet is launched and all those things. And the very weak interactions, neutrino, as I said, we look at neutrinos, observations is also one of the key observational features that people are looking at in terms of GRBs. So it has a very close connection to many of the fundamental problems in the other branches of physics as well. So it is not an isolated like one event that you study. When you are studying it, you are actually connecting many of these aspects as well. And so when did this happen? So this happened in this, the dawn of multi-messenger astronomy, as we talk about, happened in 2017. So as you know, the general theory tells that the space and time that we have started this talk with is nothing, it's not, it's more, is a curvature in what we call as gravity is a curvature in the space and time. And therefore, when you have such kind of very strong events, it can produce ripples in the space and time, and this ripples is what we kind of observe these days using gravitational wave observations. So as you can see, this is you know, a branch of how many of these events have been observed by this LIGO detectors. So we call this as the stellar graveyard, because it's after the death of these stars, these remnants are present. So we are looking at how many stars have died and what they have produced is what. So all the blue ones basically kind of represent black holes, okay, and some of the orange ones that you see is basically the neutron stars that has been. So that's a lesser number that we have seen. The ones that is shown in red here as the information that you have collected from only electromagnetic information. So you can understand this now is a new mode of information that you have, that is basically coming from the gravitational wave detections. So what was fantastic about this event that happened in 1708-17A is that everything that you theoretically expected from a model, what you expected to see was observed. Okay, so that is when the two neutron stars will come close and merge, they would produce gravitational waves. So we saw that, okay, and when they would merge, they would actually, as they come closer, they would disrupt each other, and they would like spew out all the neutron materials around it. Okay, so these neutron materials very thick with neutrons are present in that, and there is where you have nuclear fusions happening, and they form heavier elements, and these heavier elements, when they decay, you see that radioactive light is what we see as kilonova. Okay, so this is the nursery of forming of heavier elements that you see. So this is one of the places where you can see. So we know that, you know, all the heavier elements that you see on Earth has to be created somewhere in the universe. So one of the places that it creates this, and for the first time strontium is the element that has been very clearly identified. That we have seen from this that they have identified this element is formed there. So this was predicted and this was clearly observed. After and there was gamma ray burst. We expected that to happen, so that was also observed. Then the gamma ray burst will go and hit the interstellar medium, it will produce the afterglow, it was also observed. So all the 5 basic components of observations that we were expecting that we would see, all of them were observed. So to give you a timeline, so you can see that this merger point, so that is the frequency of that you know, gravitational waves goes up, it becomes the highest when they merge. That is the point that you see is the T naught, that we say the 0, the origin time, the 0 that is marked here, and after that nearly 2 seconds later you had the electromagnetic gamma ray burst emission that was observed, and nearly 12 to 14 hours later there was observation in kilonova, that is it was observed in optical to infrared. So infrared optical is where this observation happened, and nearly 9 days later was the afterglow observations happened. So you must understand that this was a huge international effort where people, you know, dedicatedly kept on observing this region, and they found this information. And there may be close to hundreds and close to 1,000 publications that might be made over this. And the afterglow of this was so fantastic. I think GMRT had observed it even nearly 3-4 years later also, they had observed it continuously till there. So this was a very fantastic event, and this marked the dawn of what we called as multi-messenger astronomy. Now it is not just electromagnetic waves from where you get information. We know traditionally we do that. Now we have informations coming from the space and time that we call as gravity also comes into picture to give you analysis ideas. So, so to just give you a perspective where India stands in terms of astronomy and astrophysics, because all the world mega projects that we have, that is in terms of whether it is gravitational waves, that is LIGO. So India is setting up its observatory in here in LIGO. One part of it will be coming up soon, and the square kilometer array is the biggest radio telescope that is being built, and India is again a part of it, where GMRT will be a part of that and will be participating in it. TMT 30-meter telescope is going to be the biggest optical telescope that will be built, and India is again a part of it. And so being part of these very mega projects, it allows us to bridge the gap in the know-how and the built information. And the most important thing is that when you are officially part of this, you get dedicated observation time and data. So you have a right to it, and it will be given to you. And the amount of data that it will be bringing will be very, very huge. And we do not have that many personnel to students to actually do this and utilize the time that will be coming to us in this picture. So I hope you guys, when you do your PhD and come back, you are in the right position to make use of some of these opportunities that will come up. And India is also in its most fantastic phase, I would say, in terms of astronomy and this, because India has entered into space missions that is meant for science. So largely we have been very dedicatedly doing space missions where that is more for applicative and other purpose. For astronomical purposes, we have now plans to expand, and as you can see, we have already done the Aditya L1 mission, the ExpoSat, and AstroSat has been already flown. It's completing 10 years now. And Chandrayaan 3 and others, which are like more science and astronomy based dedicated missions has been put forth. So which is an exciting period for the generation of young astronomers and astrophysicists in India to look forward to. So with this, I bring my talk to an end. I am happy to take questions.
Question there.
Good afternoon, ma'am. It's a nice session. And recently I heard about the issues faced by airlines. So how those issues are related to this high energy astrophysics, especially to solar activities?
Yeah, so in terms of solar activity, what happens is that your magnetic field lines of our Earth, that gets disrupted when you basically have this very strong. So most of the time we are protected is because we have a very strong magnetic field around us, and the magnetic fields can basically deflect the charges. So the charges do not basically enter here. So if you know that most of the charges actually goes and enters only in the North Pole regions. That is why you have the aurora borealis around that regions. Okay. So but majority of the other regions in the northern hemisphere or southern hemisphere, if not at the poles, you don't largely see the influx of charged particles. But now what happens is that when you have extremely strong events, these magnetic field lines are completely broken. Okay, and the charged particles enter through. So these are the events when there have been instances where you can actually see the aurora borealis as close as maybe in Delhi, and some time before that was seen, very strong events. So they come very, that is especially when you have broken this. Now these charged particles, when they come in, they can disrupt many of the electronic systems that are there in the so majority of the time that is what happens. So these electronic systems, when they disrupted, it kind of disrupts your communications systems and so on, so which kind of creates hassle for airlines and even the satellites and everything else. Every communication, your power grids, everything can get disrupted once you have very high influx of charged particles. So the best thing to protect your electronic system, sometimes what happens is to shut down. So we have something called as South Atlantic Anomaly region in the around the Earth. When you go, there is a region where there is a very high influx of charged particles. So what the satellites do is that when they cross that region, they shut down all their electronic systems, and they may come out of it, they switch it on. That is how they protect these electronic systems. So when you doesn't know that such an event is coming and it happens in abruptly, it can disrupt the communication systems, the power systems across the world, and then it kind of creates issues. So this is something that people want to invest on studying in solar weather conditions. Yeah.
Thank you, ma'am.
Good afternoon, ma'am. It was a nice talk. I want to ask that we know that black hole basically eats everything, stars and this type of thing, and that was a great event we can observe. So if we observe a event that black hole is eating Mars and stars, something all like that, in a different spectra, then can we get to know that where the Mars is basically going, or something new we can get to know about this event?
Yeah, so you are talking about if there is a black hole and the black hole is eating up the material. So, so when you say that electromagnetically, if I showed you in that stellar graveyard, there were some estimates of black hole mass that has been made using electromagnetic lights. So, electromagnetic light is not coming from black hole. Okay. As you know, black hole is not emitting as such anything. So, what is happening is when it is eating up the material, so you are actually pulling something towards you. Okay. So, when you are pulling something towards you, you are actually reducing the or giving away the gravitational potential energy. So, this potential energy gets converted into heat and more energy, which now gets visible in light. Okay. That light is what you are observing. So, from the amount of distance it has moved, how fast the energy is being produced, you can get an estimate of what is, because if you look at gravity, there is one quantity that is most, when you take potential, if you take it, you know, you can say that the mass of that object which is pulling it is the one of the main components, right, in that expression. So, you get an idea of how massive this object is, the one who is pulling this star or the other material and producing that light. So, from electromagnetic observations itself, you can get an assessment of how massive this object is, the object which is pulling that. And that is how people have made assessments that, you know, these masses, these objects are basically black holes. You can make electromagnetic observations in that fashion. But very direct observations of a black hole, you know, existence is basically now done through gravitational wave observations, where you can take direct. So, that is why you have seen the number of such observations have increased much in the recent years with gravitational wave observations. Electromagnetic, it is an inference from the electromagnetic observations. You can make an inference that the object that is actually eating up that star or the other object is basically, depending on its mass and its spatial size and things like that, we make an assessment that it is a black hole. So,
okay,
that is how we can.
Thank you.
Hello ma'am, it was a nice session. Ma'am, I recently read about white holes. So is hypernova similar to white holes, or is it still a hypothesis?
So, we have no observational proof for white holes. Okay. So, to just give you an idea of why people think, it's a theoretical idea. So, why people think is because you think about space time. Okay. So, when you say black hole, you are looking at the curvature of space and time, right. So, something that we call as warping, you might have, you know, the idea, you know, because if you think about this white hole idea, if you have seen space travel movies or things like that, the idea they talk about warping is like, you know, you take a, let's say if space is like a sheet of paper and you bend it. So, and you are saying that a black hole is where this curvature becomes so deep, like you can touch the other end of the space and time. So, let's say that if they connect, then there is like a channel between this. So, one end you go, the other end you can come out. You understand. So, that means if there exists such a, but the problem is fundamentally Einstein's theory breaks down at singularity or that point. We do not know. We have no physics. So, we do not know whether it will or not. So, you think about warping, you know, that you have heard in Star Trek and things like that. What it means? It goes that it goes through and comes out in the other point. The idea that they are using is this the point of theory that we do not know. So you can think anything, right? So they think is that if you go completely warp it, you can touch the other point of space and time. So if something is coming inside, it travels through, it can come out. So anything that is absorbing can also emit on the other side. So that emitting other end is what people think as white holes. So if such a thing exists, then you should be able to see something like that. So till now observationally we have not seen any kind of white holes. So yeah, so and as I said, fundamentally the Einstein's theory kind of breaks down at singularity. We do not have an understanding of that. So until we do not have that, this connecting would be more like a very a bit of a science fascination and yeah.
Ma'am, one more question. Black hole literally bends light. We cannot observe it, right? So how can we understand whether a black hole merges or black hole exists?
Okay. So that is where one has to correct. Black hole doesn't bend light in that sense. You have to understand this, it is the space and time itself. Light travels through space and time. Because you think about you're traveling through the terrain of the earth. So when there is an uphill, you go up, you go down, the light is traveling like that. So what is bending is the space and time. When the space and time is bending, the light is also bending. Light is in the space and time. Light is not something out of it. So it is in the space and time. We are all in the space and time. So when the space time is bending, the light is also going through that path. So it's not particularly like, it's not like you must not think it like a force. You think like that is like a force you are thinking. Somebody is pulling it apart. No, that is what is the fundamental difference from Newton's law of gravitation. When you come to the understanding of Einstein's gravity understanding is that it is not a force. It is the space-time itself. When it curves, it gives you the effect of you are going down. When it curves, you feel as if you are going down, you feel as if you are pulled into it. But it is not like that. It's the feeling that it gives us.
So ma'am, the process of spaghettification doesn't work on light, or is it also just a hypothesis?
So sorry, what is it?
Spaghettification, like when you go through a black hole, you just stretch. So light also will do the same.
So that is stretching. We are talking about stretching. It stretches because it is like, so if you take a balloon, okay, you take a balloon and you have dots on it and you blow the balloon. And what will happen? These points which first appear to be very close is still on the same points where you have walked on it. But now you feel as if as the balloon's rubber expands, these points are moving apart from each other, right? So that stretching is happening. So that is why people kind of give you an analogy of space and time like a sheet or a rubber sheet kind of, So when it stretches, the light also stretches in the space and time. So that is what we refer to as gravitational redshift. Redshift, when the train is moving towards you and away from you, it is emitting light or sound, you feel that change in frequency, right? That same thing you would experience, but not because of motion of that source. Instead, it is just because the space-time is stretching, you can actually stretch. So then what happens is the light that is coming from very, very far away in the universe, because the universe is expanding. When you say expanding, the space and time is stretching out. When it is stretching, the light when it is traveling through, it stretches and it goes into longer wavelengths. That is why the first light that you saw, which is the cosmic microwave background, it appears as in radios now at us because it has stretched through. So this you can also experience due to gravity. Now this stretching there, it is produced due to expansion of the universe. But when it comes to black hole, the stretching is happening due to the gravity of the object. So that is referred to as gravitational redshift. So you can produce redshift, that is stretching of frequencies or the changes in frequencies of light due to various effects. Due to source it is happening, we refer to as Doppler redshift. If it is happening due to the expansion of the universe, we call it cosmological redshift. If it is happening due to gravity, we call it as gravitational redshift. So you can do that with light.
Thank you, ma'am.
Good afternoon, ma'am. You mentioned that Einstein's theories like break down as singularity, right? But if I'm not wrong, they still mathematically can predict white holes like as valid, right? So I just wanted to ask if they do exist, white holes, they should be very easy to observe. So is it possible that we are observing them, but we don't know that these are white holes and these are like some other solar objects or something else?
We are observing it and we do not know if it is so. I don't think so. Till now we have any such observations that is practically, I mean, see, observations is also, see, when you predict, okay, so that is something, so I basically belong to a field where I am a bit of observational astronomist, astronomer and a bit in modeling. So when you have theories, what is fantastic about Einstein's theory is that he has very clear predictions that can be tested with observations. So when you have very clear predictions, if it is there, then it is testing with observations is more easy. Now observations has its own limits. For example, if any telescope if I take, there is a sensitivity level with which I can observe. Anything below that will not be in we cannot say it is there or it is not there. So every detector has a limitation to in its case of observations. So when there are very clear predictions, if there is a black hole or a white hole kind of a thing, you would observe it between this and this wavelengths, observations has to be in this, and then you have certain features for it, then it is easier to go and test it. Testing is not, in that way we can see whether, given the current capabilities of telescopes and whatever it is there, whether we can observe or not. Otherwise it becomes very difficult to randomly observe, because there is, as I said, there is a huge amount of data. If you look at data that is available from survey telescopes, and most of these are all survey telescopes, and they have huge amount of data that is publicly available. So, so you have to analyze it in that perspective to find out if there is any such observations, but clearly till now I am not aware of any such observations made.
Hi ma'am, I had a question regarding the GRB. Recently I read that there is a star in our Milky Way galaxy named the Betelgeuse in the Orion constellation, which is gonna get into a supernova super soon, probably. We don't know yet. So like, if it ever happens, would we be able to see a gamma ray burst and study about it?
It's interesting, but I hope it doesn't. Okay, the reason is because this gamma ray burst that you are talking about, these are extremely energetic. That means if it happens pointing towards Earth, it will destroy the whole life on Earth. It's not possible. So I'm not sure if you have seen I think in 2022 there was an event which was still extragalactic, but it was reasonably very close. It kind of ionized the upper atmosphere of Earth. It was capable to do that. So if anything of such an event happens in the galaxy and it is pointing towards us, I think it would be catastrophic. So I don't think so we'll get to study anything. That is not going to happen. And there was some years back in Nature, there was an article where they had kind of speculated that the extent of dinosaurs that have happened could be one of the possible reasons, could be a gamma ray burst event that might have happened in the galaxy. And if you think about it, gamma ray burst is an extremely rare event. It might look for us as an observer, I am seeing one event per day. But you have to take the whole volume of the universe into context to look at the total number of events. If you look in that way, it is an extremely rare event to happen. So it is not that frequent as it appears to us. It's not like
zone produce a GRP where the mass is much less than.
Yeah. So that particular star you are talking about, Orion, it's not expected to go as an GRB. It will mostly end up, if it is very massive, then much massive, such that it would mostly end up as a supernova, but maybe not end up like a or otherwise it would just die as a star like sun, forming a white dwarf and so on. So it might not fully form a event like this. So this comes under, as I said, a different category of burst where it is very, very bright.
Hello, ma'am. Ma'am, you told about neutrino productions like observation, but we all know that the neutrino is like a very weakly interactive particle. So how do you like do the observation?
Yeah. So that's a very good question. So that is where probability comes in.
Okay, ma'am.
Okay. Yeah. So it is because we take these interactions are very, very rare, but when you observe from it, and if you have very large influx of particles which are going, a finite probability of detections increases. So that is what you basically look for.
Okay, ma'am. Like one more question is like when I observed that particles like bodies like sun and neutrino stars, they produce way more neutrino production there than other particles like other bodies like Earth. So is there any connection? Why this happens? Any reason?
The neutrino productions generally, when you're talking about it, happens in very high energetic particle reactions and things like that. So for example, in GRBs when you're talking about, so if you have very explosive events, there also you might have neutrino productions, but some of the other cases is there when photons, very high energy photons interacts with matter, it will produce other particles. One of its side products is also neutrinos. So that is how you see it. So when you say Earth producing neutrinos is like
less.
You should have some reactions or some energy scales to produce what you are looking for.
Okay, ma'am. Thank you, ma'am.
Maybe the rest of the questions you can ask at lunchtime. First, let's.
Come this side.
Yeah.
So token of
memento.
appreciation from Resonance, copy of Leela.
Yeah, please come in quickly. 2:30 session starts, means be here before 2:30. We should start the session, not walking the time. This is something we have to be particular about. No? We've been saying so many times, and also phones silent mode or whatever. Okay, welcome, and afternoon session today. We have one talk followed by another very interesting item which I'll announce after the talk. So the talk is by Professor Srilash. We are very glad to have him accept our invitation, and I invite Professor Mahesh to chair this session.
Good afternoon to all. We have with us this afternoon Dr. Srilash, who is a scientist at National Center for Earth Science and Studies, NCES, which is not far from here. He has done his PhD from Indian Institute of Science and has done postdoc at INRA, France. And he'll be talking to us on a topic related to hydrology, as he himself is a practitioner of environmental hydrology. Dr. Srilash, over to you.
Good afternoon to you all. I will speak on a different topic from what we have heard in the morning session. We went to astrophysics, space, and some mathematics. Now I bring you down to earth with something on the so-called critical zone. I will tell what is critical zone, and it's kind of an interdisciplinary subject that I know you are from different backgrounds. Some of you might have already learned components of this. Some of you may be able to use the tools that are available with you or the skills you are having to work on some of the problems that comes under this critical zone science. Okay. So I will give you the definition. So like I said, I am from the National Center for Earth Science Studies, and I will talk about my center a little later. So what is this, the so-called critical zone? That's what we are here. And if you cut a slice of the earth, you have several layers like inner core until the mantles, and then you have the earth's crust, and then you have the several atmospheric layers. So what we are going to focus is on this upper crust, where the changes are dynamic and very most active. So it will be something like this. Above the upper mantle, you have the crust, and then you have the living layer, where we have all the living organisms. Majority of the living organism that sustains on this zone. It includes the atmosphere part, the canopy part, the near surface part, the subsurface part, vadozone until the bedrock and the aquifers. Okay. Now, the concept of critical zone evolved probably in early 2000. Previously, people were talking about pedology or soil science as a separate subject, and then it becomes hydropedology. They added soil and water together, it became hydropedology. And then slowly people talked about the critical zone, because other than just soil and water, there are so many interactions or processes that takes place in this zone. We can talk about biological activity, we can talk about the exchanges of energy, nutrients, fluxes within the zone. So that is why put together everything, this term was coined in the early 2000, and in United Nations they started this so-called critical zone observatory programs in the early 2000s. So as the definition says, it is the thin layer of the Earth's terrestrial surface. You can assume it as the skin of our body. Okay, it's very thin layer. Actually, this is the place where much of the activities takes place on the Earth. I mean, dynamics of the Earth takes place much in these zones. And that is why there is a renewed interest or a new interest in studying this process. What are the processes that is taking place in this zone? How long this zone can sustain in the terms of forcings, like anthropogenic forcings or tectonic forcings or climatic forcings. What is the tipping point at which this so-called critical zone will fail? So to understand all these things, we need to study the processes, we need to monitor the processes, we need to model the processes, and then understand how these things functions. Now, coming from the definition, this is how a typical critical zone looks like. You see the bedrock, and then the weathered part, and then the soil layers and the canopy to the atmosphere. So there are several processes that are taking place in this. For example, you are seeing the soil as the major component of the critical zone. Then you have the hydrosphere, biosphere, lithosphere, and atmosphere interacting continuously within this zone, and that is why we call that as a critical zone. Now, in critical zone, you can define in two types. Like we have pristine systems, like for example, an undisturbed forested ecosystem where you have the processes which are taking place in a natural way. And then you have highly managed or human modified landscape. Again, there is another critical zone which is managed by human through a lot of anthropogenic forcings. So the idea is to see how the critical zone reacts in two different systems. This is the forcings I have been telling. What are the forcings that pressures the critical zone to change the way it functions? What is the climatic forcings? You can either say the present climate or the future climate or whatever, but that's the forcing variable that is coming into the system. And then you have man-made changes, that is anthropogenic forcing, and then the natural tectonic forcings. Now, since I told it is the top of the canopy to the bottom of the aquifer, it is not a single subject. It is a multidisciplinary or a transdisciplinary subject. So that is why I brought this topic to present before the students, because there are two things I want to focus. One is working in a transdisciplinary or multidisciplinary environment rather than an isolated one. Second one is I am a basic experimental hydrologist, and then you see that not many people are there in the world who are actually doing experimental works or generating their own data, because a lot of data are available in the open source and people start using that. But then there is a thrill in creating our own data, going to field, making measurements. So I want at least some of you to be in this field, so I thought I will present it in this way. So you see, I am a hydrologist, so I start with hydrology, and then geomorphology, geology, hydrogeology, biogeochemistry, geophysics, and there are several multiple components or multiple specializations of people who work together in this, the so-called concept of critical zone. Okay. So I cannot study water as a single component. I need atmospheric inputs to see the kind of water that is coming from the atmosphere. I need to see what happens to each drop of water that is falling on that surface. How much fraction of it is going back to atmosphere, how much fraction of it is going to the groundwater or as a recharge. how much fraction of this is going back to the ocean as submarine groundwater discharge. So to understand all these things, I also need the help of other disciplinaries. So there is critical zone studies are usually taken up by a multidisciplinary team. There are several people with multiple expertise working together. There is another thing in this critical zone. The complexity in the critical zone is that we talked about the several processes that takes place, but then this happens at different spatial and temporal scales. Okay, so that is another challenge. For example, you talk about weather like rainfall, snow melt, evapotranspiration, that takes place at catchment or watershed or catchment scale, and it can, from minutes to weeks, it can happen. But if you take a solute transport or movement of a solute from the Earth's surface to the soil layers, or the percolation of water, rainwater from the surface to the Vadose zone, so those takes place within minutes, hours, or days. But then there are processes which takes place at a decade or centuries or millennia. For example, the soil formation process. You know that soil forms through a rock weathering process. So that doesn't happen over last 10 years, 20 years, 100 years. It is a millennial process. Okay, it takes over several centuries and several millennia. So the temporal scales and the spatial scales are different for each processes. And that is why you need to have multiple kind of measurements at different time scales to understand the critical zone processes. Now you assume this critical zone as a reactor where so many reactions are taking place. So for example, this is the critical zone. This is kind of a reactor or an engine where you have energy storage, energy and matter flux, the exchanges between the atmosphere and the subsurface, and the product that is generated from the so-called reactor. Okay. Now you have different cyclic process that is taking place in this the critical zone. You can talk about the hydrological cycle, you can talk about the carbon cycle, you can talk about the nitrogen cycle or the biogeochemical cycles as a whole. But if you think all these cycles are taking place in the so-called small layer or very thin layer. So if you ask what is the depth of this so-called layer, it can be few meters to few hundred of meters depending on the landscape in which you are working. So if you go to a top of a mountain, you see a bedrock and there is hard rock and there is no critical zone. But critical zone has a soil, and if you come to the valley, you have a depth of soil, for example, 2 meter soil depth, and then you have vegetation, and then you have the parent rock and the aquifer. So this critical zone, by definition, the depth varies from few meters to few hundreds of meters. Okay. Now soil is an important component of the critical zone, and you see the soil as a single component has multiple role in the critical zone. For example, this allows filtration of water to the subsurface. There are several nutrient transformation, nutrient storage, carbon and nitrogen storage that is taking place in the soil layer. And then you see the soil formation taking place from the weathered zone to the organic matter and the top. And then you see a cycle of nutrients from the weathered product to the soil, and then that is finally feeding to the canopy. The canopy also have a big role, or canopy or vegetation has a very big role in this the critical zone. You see the root water uptake, or the process in which the water is taken up from the soil through the plants and then again released to the atmosphere as evapotranspiration. Okay. So that is a very important component which takes place in the canopy. And then the nitrogen fixation, soil biomass production, organic matter production, everything happens in the canopy environment. Then there is a water component. So you know the global hydrological cycle and what percentage of water we have with respect to the surface water and ocean water that is available. So the water that is coming from, for example, in this part of the country, the only water that is available to us is through precipitation. So you know how much part of that precipitation or rainfall is going as surface runoff or flowing through the surface, how much part of it is going to the root zone or the Vadose zone, and how much part of that will reach the water table, and what fraction of this water will go back as evapotranspiration, and what fraction of this water will go as base flow to rivers and also submarine groundwater discharge to oceans. So there is several processes that is taking place within this compartment. Now then there is linkages between, for example, if you take the groundwater process, there is several linkages within this water cycle itself. Okay. So groundwater, if you take the chemical constituents of groundwater, then it is intricately linked to the geology of that region. Okay. And then how much water is available as a groundwater again is links to the aquifer characteristics and also the input that is coming as rainfall. Okay. Now we talked about the several processes that is available, like we talked about canopy, we talked about soil, we talked about water, there are several things. But how do we measure, monitor all these things? Because I keep telling that this is a multidisciplinary thing, but how do you measure all these things? Okay. So that is where the concept of the critical zone observatory comes. Okay. So what you do here is that you make an area, it's a watershed or a small sub-basin or whatever it is, and then you heavily instrument it to monitor or measure the process that I have been saying. For example, this is a typical schematic of a critical zone observatory. Okay, the observatory which monitors the Earth observation. That's what we call it as critical zone observatory. For example, you have a stream gauge which measures the surface runoff, that is flow of the water through the surface. Then you have groundwater loggers which measures what is the water available in the groundwater. Then you have a flux tower that measures the carbon dioxide and water flux that is going from the surface to the atmosphere. And then you have radar measurements, you have canopy measurements, you have sap flow measurements, and then satellite is looking at all these things. So you have satellite data of all these processes. Okay, this is how a critical zone observatory looks like. And now if you look in like 10 years back, 2016, this was the global status of critical zone observatories in the world. You see much of the critical zone observatories are focused in the continental US and also the European Union. But then there are very limited observatories in the tropics, and we have one observatory in India. Now, if you look at the USA, they have a critical zone network called CSET, critical zone network. They have several observatories spread around the continental US. And then you have the French observatory, which is called as OSCAR. They have multiple observatories in French. And then Terino is the German observatory. They have multiple sites where the critical zone processes are being measured in the German thing. So now, how do people decide, like, where do we set up these critical zone observatories? So that is where this concept of environmental gradients come. Okay. So we talked about the natural disturbance and anthropogenic disturbance, like a pristine system and a well-managed system. Okay. So that comes as like disturbance. Then you have the lithology, which is the geology, different kinds of geology. Topography, you have the climate, for example, from a humid to semi-arid to arid kind of climate. The time scales of the process which you want to study, and then the biological components. Okay, see, these are the different environmental gradients, and based on these environmental gradients, we are setting up observatories. This is the distribution of the critical zone observatories in France. If you see, it is a lithological gradient, it's a climate gradient, and then they talk about the pristine systems, agriculture systems, and then again, different land use categories. Okay. So this is how the critical zone observatories are distributed worldwide based on the environmental gradient that exists and what kind of processes we plan to study there. Now there are several instruments and processes that we measure. For example, I start with soil. There are different experimental processes that we do to characterize soil. So soil have like physical characteristics, chemical, you can say engineering characteristics also, and hydraulic characteristics. So we have a set of instruments. For example, this is infiltrometer. Some of you might have already known this, infiltrometers, lab scale, and also we can do that with smaller instrument at field scale. And there are several physically, like augers, where you can physically disturb the soil and take out the samples and do the analysis in the lab. Then, for example, the moisture, the water content in the soil, you can measure in situ with things like surface soil moisture at top 5 to 7 centimeter soil moisture. You can also have a drill hole and make the measurements at multiple depth. And then you have advanced sensors which can give soil moisture at space and depth time, average soil moistures. Then you, for hydrometeorological measurements, you have the automatic weather stations, you have the pan evaporation meters. For the surface and groundwater level, you have the radar velocity meters which are measuring the flow of the streams. And then groundwater loggers measuring the water level in the groundwater systems. Then you have the sensors, sondes, which measure the hydrochemical characteristics of both surface and groundwater systems. And then for evapotranspiration, you have the so-called lysimeters, which is kind of weighing type, like measuring the soil-water balance, and then that gives you an evapotranspiration, that is the volume of water that is going from the Earth's surface to the atmosphere. Then you have this kind of canopy monitoring. Canopy vegetation, how do you monitor? You have some terms like biomass of the vegetation, leaf area index, and then crop height. So vegetation water content, these are some of the characteristics of the vegetation which is measurable. Okay. For example, this is the measurement of leaf area index. That is, this is NDVI. We also have chlorophyll measurements. We also have biomass measurements. So all these measurements characterize how a vegetation grows, what stage it is growing, and how these are the parameters or variables that we feed into the model. Okay. when we tell canopy modeling, these are the variables that goes into the modeling to see how the vegetation reacts to, for example, crop water stress, how the vegetation reacts to different nutrients, how the vegetation reacts to different kind of rainfall. And now we also measure the fluxes that is taking place from the earth surface to the atmosphere, whether it is water flux, carbon dioxide flux, there are measurements of nitrous oxide flux, methane fluxes. So there are several measurements type that is available. I start with the one observatory, that is the Kabini Critical Zone Observatory, which was India's first critical zone observatory, established sometimes in the mid 2000s. Okay. So like I said earlier, in the tropical regions there are very less critical zones as compared to the temperate region. The tropical regions are more sensitive. You have a monsoon system which has a variability within itself. There are long periods of rainfall and then long periods of dryness, and then often heavily dense populated. Then you have alternate heavy rainfall region and the temperature, so it makes the weathering process very intense. So even though the processes are fast in the tropic, not much critical zone observatories are there in the tropics, and the first observatory is the Kabini Critical Zone Observatory, set up by Indian Institute of Science, Bangalore. So I did my PhD in this Kabini Critical Zone Observatory. This is a part of the upper Kaveri basin, and if you look at the observatory, you have a region where there is 5,000 mm rainfall in the Wayanad region, and you see, as you move towards east, the rainfall reduces to 900. This is around the Gundalpet, Mysore region. Okay. So there is a large scale variability, like within 40 kilometers you have a variability of rainfall from 5,000 mm to 900 mm. Okay. And then to study the different processes, different types of watershed, different scales of watershed have been taken. For example, the Mulehole watershed, which is inside the Bandipur forest, it is 4 kilometers square and it is fully forested. It's a pristine ecosystem. And then you have a Berambadi watershed which is 84 kilometers square, and in that you have a sub watershed which is Madur, which is partly forested and partly agriculture. So different processes are studied in different scales in these watersheds. Okay. Now this is what I have been telling. In a very small distance, the rainfall changes from like 5,000 mm rainfall to 900 mm rainfall. So there is a large climatic gradient. So landscape wise, you see the western side, you have a rice, tea, agroforestry. This is the humid part of the watershed. And then the mid regions, subhumid to semi-arid kind of regions, you have the forested, the Bandipur and Mudumalai national parks are here. And then you have the highly irrigated, the Kaveri region where you have rice and sugarcane, and then there is a semi-arid dry land agriculture kind of thing. So within a critical zone observatory, you have different kinds of land use or managed systems. So that gives an opportunity for you to study different processes at different scales and different gradients. Okay. Now coming back to what we have been doing. So as I said that the observatories in the tropical regions are very less, and that is why we started going for this terrain. It is called Tropical Ecosystem Research Observatories in Peninsular India. NSES created a network of observatories in South India. So I come back to NSES. We are under Ministry of Earth Science, Government of India, and NSES is located in Thiruvananthapuram. We are an Earth Science Institute, so we have multiple disciplines like solid earth, environmental hydrology, marine science, atmospheric science. So I belong to this environmental hydrology group. And we choose this southern part of India as the place where we are going to set up the observatory. Okay. Now we have 3 observatories. One is Attapadi, which is the Palakkad-Coimbatore border after the Palakkad Gap. This Palakkad Gap is here. And then you have the one in Munnar, which is high altitude mountainous watershed. And then you have in Aduthurai, Tanjavur, that is the Kaveri Delta region. So you have the observatories from the high hills to the valleys. Okay. Now why did we choose this part? Because you see this heterogeneity in the characteristics. You see the rainfall in the Western Ghats, it is high rainfall region, and then the rain shadow region, and then you see arid and semi-arid kind of settings. And the lithology is also very complex. The geological terrain is different in the different observatories. And also you see the drainage pattern. For example, the Kaveri River, the drainage is very long. But if you see the rivers flowing on the Western Ghats in the western side, these are very small rivers. So these rivers have very less residence time, while the eastern side rivers have large residence time. So the process associated with this also varies. For example, what happens to the drop of water that falls on the eastern side, and what happens to the drop of water that falls on the western side, how fast it moves to the ocean, and what are the chemical reactions that takes place because of this pattern of the flow. So that is why we created this observatory to understand the relative influence of natural perturbation, which is basically the climate variability, and also the anthropogenic activities on hydrological and biogeochemical cycles in the different environment gradients along the peninsular India. Okay. Now there are several science questions that we had when we started making these observatories. Like one thing we were looking at is how the hydrological cycle is getting accelerated under climate change. How fast is the hydrological cycle moving as compared to like 2-3 decades back. And then we also looking at how this remote sensing platform, for example, now there is a NISR satellite which was recently launched. There is a Trishna satellite that will be launched next year. So how these satellite data can be calibrated and validated, and how this data can be used to understand or upscale the critical zone processes to different regional scales. Okay. Now I talked about the gradient. There when I was showing the 3 observatories together, I told Munnar is a high altitude humid observatory, Attapadi is a subhumid to semi-arid transition observatory, and the Thanjavur Aduthurai observatory is a tropical wet and dry type climate. But if you look within this observatory also, there is large scale variability. This is the Attapadi critical zone observatory. This is part of the upper Kaveri basin, and this is Munnar critical zone observatory is a part of Periyar and Amaravati river basin, and this is the deltaic part of Kaveri. So the landscape is also different between these observatories. This is majorly paddy and sugarcane. This is forested and plantation type, and this is dryland agriculture type of. Now, if you take the Attapadi critical zone observatory alone, you say large variability in the lithology. Geology is also there is different, and the rainfall pattern you see there is high rainfall region to low rainfall region, and the temperature also is different. So between the observatories there exists a gradient, and within the observatory also there exists a gradient. So that makes us ideal to study the different process, how each processes takes place in the different gradient, and how the gradient controls the critical zone processes. Okay. Now this is how a typical critical zone observatory this is from Attapadi. How does it look like with so much of instrumentation put together and measuring variables at a different spatial and temporal scales. Okay. So we work on hydrology, hydropetrology, hydrochemistry, biogeochemistry, remote sensing, and then use several machine learning and modeling tools to understand the different processes that is taking place in this critical zone. Now we make multiple measurements, like we make the measurements of canopy, we make the measurements of atmospheric variables, we make the measurement of soil, the bed ozone, evapotranspiration. These are some of the instruments that are set in place in the so-called critical zone observatory. This is the Attapadi critical zone observatory, Munnar and Aduthurai, and then this is automatic weather stations, soil moisture sensors, weather stations, lysimeters that are placed in the observatory to measure the processes. This is the cloud microphysics observatory in the Munnar high altitude region, where you study the physics of the cloud. And these are the different field experiments that we carry out in these observatories. So the setting up an observatory takes some time. You get connected with people, get there into confidence, because these are installed in actual farms in a field of the farmers, not in the campus of some institute. We do it in the real world. So the processes what we study also represents the real world factors. Okay. So there are multiple teams involved in setting up this observatory. This is a recent one. We set up a scintillometer, that is a tower to measure the energy and water fluxes. Now you see the contrast between the same observatory taken in October and March. Okay. So this kind of contrast you have within the observatory, like in a time scale. What we talked earlier was a spatial, at spatial scale what is a gradient, but in the temporal scale also you have this kind of gradient from a extremely dry in March to a high greenish in the October, just after the monsoon period. Okay. So this gives us the scopes to study the processes taking place in the different temporal scales. Okay. Now there are several measurements which we take. Some measurements are made at minute, every minute we measure. Some are made at half an hour, 1 hour. Some are measured at daily, some are measured at seasonal, some are measured at monthly scales. Okay. So these are the several variables which we measure. There are several instruments which record these things automatically, but then we also go to the field continuously for generating much of the data. For example, the soil experiments, we bring soil samples to our the ANSYS laboratory at ANSYS to experiment with soil physical and hydraulic functions. But for example, you take the hydrochemistry, you are studying the hydrochemistry of the stream. So you go to the field monthly or seasonally, bring samples and then analyze it in our laboratories. But for example, the soil moisture, you measure it on site, having an instrument, you measure it on site and you can measure that soil moisture at different depths or evapotranspiration or atmospheric variables like rainfall, wind speed, wind direction that you can measure at every minute. These are automated sensors which keep measuring and transmitting soil physical, chemical and hydraulic characterization. So bring the kind of semi-disturbed cores to the laboratory and carry out the analysis. Now I will point some of the research, like one way to look at is like see the research in critical zone can be taken in two ways, like you generate a hypothesis and work towards that. Other way is that you generate a data, sit with the data and find some answers. Okay. So both ways work. So I took the second way, that you generate a lot of data, look at the data, and if the data do not follow a pattern, then you investigate why it is so. Okay. The difficulty with the first one is that you generate a hypothesis and work towards that. That means you are focusing on a single point, you are not looking at the surroundings. So instead you measure all these variables together, whether it is canopy, atmosphere or groundwater, surface, anything you measure, or use geophysics, everything you measure together, bring the data to your office and then sit with the data, you see some unusual patterns in the data and then investigate what is happening there. Okay. So I'll quickly say some of these things. See, one question that I always had, I mean even now it is not answered, is like how can we accurately estimate subsurface properties? What we can see is from the surface. Even the remote sensing platforms give information about only the top 10 centimeter. You can't have information beyond that layer. So how do you estimate soil properties or soil characteristics beyond that layer? I'm not talking about point scale, at spatial scales. Okay. Now, if you look at the soil maps that are available to us, it is basically the surface soil maps that is available from NBSS or other global data sets. But when you have a multi-layered system with a different type of soil systems, how do you characterize this? Now, the question is, why do you want to characterize? So why surface is alone not sufficient? Because see, much of the process, for example, evapotranspiration takes place from the deeper layers because the canopy grows from that layer. So you need to have a quantification of the volume of water that is going to the atmosphere, because that is also very important for numerical weather prediction models. To have a better prediction of local scale weather, we need to have the hydroclimatological variables also, or land surface variables also to be estimated at finer accuracy. Okay. Now the challenge is, how do we estimate this multi-layered soil system? Okay. So there have been different hypotheses and being tested. Now why that is of interest is like, so if you take soil moisture, that is the soil water content, the water that is available in the soil, this has different, the variability is in all scales. You go in X, Y, Z direction, it varies very fast. And also the controls of soil moisture, what controls the soil moisture at a point scale, at a plot scale, and what controls the soil moisture at a regional scale or watershed scale is different. So the spatial and temporal controls of the soil moisture are different, and this has very high variability. You measure soil moisture in the morning, in the afternoon and evening, that has a different value. Okay. So that is why we need to characterize the soil properties. Okay. Now we did some experiments and we generated a lot of data that's coming from the field and put the data together, and you see some patterns that is coming out from the data. Okay. So this is the correlation coefficient between the variability of soil moisture with soil type, that is I put here clay, and also with canopy. Okay. So you see there is a decreasing influence of clay content with soil moisture variability when you go from surface 10 centimeter to the root zone 80 centimeter. But then the leaf area index, influence of the leaf area index is increasing. That means the canopy holds much more information of the soil moisture than the soil physical properties. Okay. So this data is telling us, I mean we did not have a hypothesis for this, but the data is showing that. Okay. So then we run a sensitivity analysis using model to see this behavior over temporal scales and to see how the soil, different soil properties are acting in different periods of the crop growth stages. Okay. And then we run models to see, for example, this is sunflower, sorghum, and turmeric and maize. We run models with the different water conditions and see this is a leaf area index. Okay. How does the leaf area index vary with water stress? Okay. So from this we can understand that the vegetation holds much information about the subsurface soil characteristics than the soil physical characteristics. Okay. So then we brought the concept of vegetation as a sensor for estimating subsurface soil hydraulic properties. Okay. So the question is, why can't we use vegetation? Because vegetation is the one that is available in the surface. We can easily monitor that. Remote sensing platforms are there, which is measuring leaf area index, which is measuring NDVA, biomass, evapotranspiration, etc. So why can't we use those information to find out what is in the subsurface? See, these properties of the soil doesn't change over time. I mean, for at least for 10 years, 10, 15 years, it is relatively constant unless there is some external disturbance that you put in. Otherwise, this is kind of a static property. Okay. So now we build methods to answer the question. Like if you take a surface hydrology model, you use the satellite soil moisture, you inverse and you can get the surface soil properties, but you can't get the subsurface soil hydraulic properties. That is where you bring in a crop model. Crop model models the canopy very well, where a surface model takes it's an empirical component of the model. Okay. For example, the Hydrous model considers, Hydrous is a Wadowson model which considers canopy as an empirical component or through empirical functions. But when you actually take a agrohydrological model or a crop model, that has well-defined crop functions, crop water functions. Okay. Now, use the same principle here. You use the crop model instead of hydrological model. You use the canopy variables like leaf area index or biomass or AT, evapotranspiration. Use that in a crop model, do inverse modeling to estimate the soil properties. Okay. This is what we tried. And then there is the methodology development that comes along with it. You do some Bayesian inversions, generalized likelihood uncertainty estimators, etc. And then finally, I'm not going deep into the method, but finally you will end up with observations that you are hypothesizing. Okay. Here, for example, if you look at this plot, SSME surface soil moisture, when we use surface soil moisture, we are getting the first layer property very well, but we are not getting the second and third layer well. So, I mean, subsurface is poorly estimated. Okay. The first column is the surface, next two columns of the subsurface. So, this is expected because surface soil moisture will have information only about the surface soil properties. But if you take canopy variables like biomass or leaf area index, you see a reverse pattern. You don't get information of the surface, but you are getting signals in the second one. So now you combine surface soil moisture and biomass, surface soil moisture and leaf area index, you are getting signals in both layers. Okay, this is what we are expecting. What from the hypothesis of vegetation as a sensor, we expected this and we are also getting signals from there. Now, the hypothesis that vegetation can be used as a proxy for estimating subsurface soil hydraulic properties is proved through a set of synthetic experiments and modeling runs. Now, these are all done at point scale and we need to do it at spatial scales, and now there are tools available with us, machine learning approaches are there. We have the hypothesis, we have the physics based information. Now you put it in the machine learning models and then you create maps. For example, one such initially generated maps looks like we will have subsurface soil hydraulic properties at spatial scales. This is a heat map showing which variables. This is field capacity of first layer, second layer, third, and wilting points, and different variable combinations which gives the best estimate. Okay. Now the idea here is that using leaf area index, biomass, or evapotranspiration is giving you a good chance to estimate the subsurface soil hydraulic properties. So this information came from the data that we generated. Looking at the data, you have an idea that this is going to happen. Okay. Now, moving away from the hydropetrology part, you also have this different chemical and biological process that is taking place in the observatory, and you want to know what is the control of these changes in the chemical and biological processes. So we have these two studies carried out at Attabadi Critical Zone Observatory on groundwater and also the stream water. And you see that the climatic gradient, this is the high rainfall region and this is the low rainfall region. So you also see the solute concentration also varies from the climatic, so that climatic gradient is controlling the groundwater chemistry and also the stream water chemistry in this observatory. Now you look at how this hydrological cycle is getting accelerated over time. Okay. We talked about climate change, but you also have to look at how this hydrological system is reacting to the climate change. How fast is the cycling of the water takes place. Okay. The rainfall is happening. There are extreme even rainfall. That means much of the rainfall is, or water is coming in a much faster rate to their surface. And if that happens, then much of the water is going as runoff back to the ocean. But then there is a component of evapotranspiration, recharge, and then again submarine groundwater discharge, that is the groundwater that is flowing into the ocean. And how the intensification of hydrological cycle is taking place in this observatory, that also you come back with the data set. You are seeing the changes in the groundwater level, you are seeing the changes in the evapotranspiration, that how fast evaporation is taking place, or how fast the groundwater levels are changing, and what is the flow pattern in these rivers, what is the connection between the groundwater level and evapotranspiration. Evapotranspiration and groundwater level is generally connected because vegetation is the factor which takes the groundwater, converts it to evapotranspiration and gives it back to atmosphere. Okay. And we study the data from long period to see what kind of changes is taking place in the recent years as compared to what has been taking place in the 20, 30 decades back. Okay. Now with this understanding, we move forward with developing some tools for studying this process as a whole. See, people have been studying surface hydrology and subsurface hydrology as separate isolated components. Okay. There are specialist people for surface hydrology and there are specialist people as groundwater modelers. Okay. But now in the present situation of this high intensity rainfall events, you cannot actually separate these two things because you see what happens to the water in an extreme event and what happens in a water in a normal rainfall event. Extreme rainfall event generates a lot of runoff than recharge. In a normal rainfall, it creates more recharge than runoff. Okay. So what happens is ideally we consider recharge to groundwater as a fixed fraction. For example, we say 15% of the rainfall is going as recharge. This is what Central Groundwater Board says, and that is what we assume in doing modeling. But now the recharge factor itself has become dynamic, as is the rainfall. Okay. With the different rainfall intensities, you have different recharge factors. Okay. So if you want to take all these things into account, then you need to do an integrated modeling. That means you have to bring the surface component into the subsurface groundwater hydrology. Okay. So either there are several existing models which does, and also, but we can also create models with our own tools available to see how these interactions are taking place at different scales. Now, we are also focusing on the biogeochemical processes, how the climate change and anthropogenic forcings are changing the biological or biogeochemical process in this watershed. But this is one study that we are continuing in the Attapadi and Munnar Critical Zone Observatory, where we are looking at the carbon dioxide uptake, dissolved organic carbon and particulate matters, how these are changing, and what is the factors that is controlling, whether it is climatic controls or anthropogenic controls. And then another important component is the concept of critical zone from space. There is a concept of hydrology from space, that you monitor the hydrological variables from space. Moving one step ahead, we say it is critical zone from space. There are multitude of satellites that is looking towards Earth, like Earth observations. So much of these variables we are also measuring in the field. So there is now a synergy between what we measure in the field and what the data that is coming from the satellite. So now we have the opportunity to calibrate and validate the satellite products. For example, the NISR, the recently launched NASA ISRO's synthetic aperture radar, which is going to generate soil moisture at 100-meter resolution. So our observatories, these Attapadi, Munnar and Adudur observatories are also part of this NISR CalVal program. We have set up sensors in these 3 locations in gridded way, so that the NISR data, when it comes to us, will be calibrated and validated and will be ready for use for the public. Okay. The same way, there is a Trishna satellite that is going to be launched next year, that comes as a thermal satellite, which will be useful for evapotranspiration estimations. And we are also having several flux towers installed across these observatories, which will add to the Trishna satellite mission. Now, if you heard, there is a monsoon mission. Some of you might have already heard. The Ministry of Earth Science has launched a big program on enhancing the weather prediction at local scale, or they call it as weather management, going towards weather management. So in tune with Mission Mousam, we are also expanding our network, observation network in South India, with flux towers, weather station, soil moisture sensor, and evapotranspiration sensors coming up at big scale in the southern part of India. Now this is from 2020. From 2016, where we have 1 observatory, now we have like 9 observatories in India. There are still a lot of gap areas. For example, the Andhra, Orissa region, arid region is not covered, and then you have the desert, dry desert and wet desert, and then you have the eastern side. There are a lot of places where the gradient exists, but we don't have measurements of these atmospheric or critical zone variables there. Okay. And our aim is to create a terrain network of observatories in India. From CZNet, OSCAR, Terino, we are going to have a terrain network in the near future together with Mission Mousam or Monsoon Mission. We will have a set of observatories. So there are several publications that came out of this study, and as I said, this is a multidisciplinary study, so you can see publication in hydrology, you can see environment science, you can see geology, biogeochemistry, so there are so many publications that come together. The point is we have to sit together, bring all these things to bring out an understanding of the system that we are looking at. So I said like it's a multidisciplinary team, so we also have a multidisciplinary team which have geologists, geophysicists, hydrologists, hydrogeochemists, and there are several students and project staff with multiple discipline background working in these observatories. Okay. Thank you.
Thank you, Dr. Srilash. We'll have some questions now.
Good afternoon. Thank you for the wonderful talk. I was wondering actually, earlier you mentioned that before this project, Terrain, there was only one critical zone observatory in Kabini, right? Why, I mean, it's an ecologically rich environment, especially in India with such a diverse, I mean, there's mountains, there is plains, you have deserts, tropical. If it's such a hotspot for, so to say, it's a good critical zone, why is there no more critical zone observatories?
Okay, you remember I told you like not many people are interested in field hydrology. Okay, see this involves a lot of effort that you are buying instruments, you are putting it in somebody's farm, someone's land. So there is a chance of this being destroyed or being stolen. Okay, so the asset finally, like even though it's Government of India's property, it's me who buy these instruments and put in the field. So I am responsible for that. And then the amount of effort that is required to go to the field, collect the data, do some experiments, that is actually huge. You need a set of people who are actually interested in going to the field and making these measurements. That is why you don't see much observatories in India. Okay. That is the first point. So the Kabini Observatory started in mid-2005 in collaboration with the French team. French team already have an experience of setting up observatory, the Oscar Observatory in France. So they came to there is an Indo-French cell in Indian Institute of Science, Bangalore. So even now they are there. So that is how the first observatory started in India. And I studied from that observatory. I did my PhD in the Kabini Observatory. I have the understanding of how an observatory works and how to set up the observatory. I came out and I set up three more observatories there. Okay. So one of the point in bringing this talk to you is to encourage some of you to come to field to make real observations. See, much of the people who do work are using secondary data. Someone's generated data, reanalysis data, model data, and you look at the data and do it. Nothing wrong in that, but I'm telling the real data, you go to field, you measure the thing, you see processes, you measure, that is a different kind of joy. Okay. So that is what we are doing, and you see very limited number of people will be interested in going to the field. I mean, the luxury you sit in an office in a computer in an AC room, you don't get that in field. You have to run in sun, rainfall, etc. So I think it is more on the availability of the people to put these observatories in the field. That is why we don't have much observatory in India.
And as somebody who is greatly interested in fieldwork like this, what would you suggest is the pathway to take to eventually reach like how you did your studying from there, and now you have set up 3 more observatories? As somebody who is greatly interested, what like do an internship at one of these observatories? Like what is the path to take? What to do?
You are from ISER?
No.
Okay. See, internship, like NSS always calls internship twice a year, and you can always come and do. That is one part. But these observatories are also open for everyone. I mean, I collaborate with ISER here in Dr. Prashant is there, and then IIT Palakkad, IIC Bangalore, then space applications. We have so much collaborations because, like I said, this is too big a work that I cannot be sitting alone and doing. Okay, so for example, IIT Palakkad students are working in the Coimbatore Observatory. So in that way, anyone interested can come. You can do experiments, that is one part. But you are also free to use our data and come out with something. We are also generating a lot of data, but someone has to sit and work on the data also. So in both ways, it is open.
Thank you, sir.
Before somebody asks, I just want to add to this that at 4 o'clock we are going to have a kind of a meeting, conversations with the scientists. We'll make groups. At the time you can ask more about the pathways and so on. Okay? We will have more.
Sorry, just the picture that is there.
Sir.
What do those wires do? Are they carrying something?
No, no. Actually, another challenge on this observatory is this animals. Okay, this is a highly elephant disturbance area. Okay. So when we set up this observatory, we had this thought of putting an electric fencing, so that at least our instrument will be free from elephant attack. Okay. But we never put a electric supply. It was just that fencing we made. This is the typical fencing of this for elephant protection looks like. No, no, this is the angle, I mean camera angle. Actually this is not that high. See, the tower is much higher actually. Maybe there was another. It's the same picture, sir. This is the height of the tower and you see the fencing something like this. So these wires actually is that elephant's trunk, no? They can enter there. So it's all electrical things. So this is typically how the fencing for protecting against elephant looks like.
Good evening, sir. It was a nice session. So my question to you is, are there any limitations of using vegetation as a sensor for environmental monitoring?
Yes, depending on the problem that you had. For example, what I have been talking is on water limited condition. Assuming that nitrogen or nutrient supply is proper, I assumed that condition and I assumed water limited condition to do all this testing. So in case there is a nutrient limited condition, the crop behavior will be different. Okay. So depending on the problem you are looking at, there are challenges. Of course, there are challenges. That is why you need to generate data set and then look at and then see how to address it. Okay.
Thank you, sir.
So do you showed long-term data from 20, over many years, right? In one of your slides. Do you have that kind of data for the plant, the canopy information?
No, these are data from 2016
Okay.
when we started.
Right.
The atmospheric variable that you saw was from IMD, our sister institution's data, long-term data. But some of these variables like canopy or soil moisture, this happens after 2016 when we started setting up this observatory.
Okay, just follow up on that. Do you expect to see, because you have different crops, I think, that you're growing, right? Data on different crops?
Yes.
So how does it affect the soil? Are you trying to monitor, do you monitor that
No,
as
we did
well?
not look at that angle. I mean, we need some agronomy, specialist in agronomy coming towards this to look at it in that way. I am looking at the other way, how soil affects vegetation, and how vegetation affects soil is a different thing that someone with that expertise should be available to look at that angle. Yes, we haven't looked at it yet.
Yeah, I have a question. So I see there are many observatories throughout the earth, right? Everywhere in every country. And I can imagine that overall geological features must have lot of commonalities. Like if there is some zone in India, there should also be parallels in Africa or South America, wherever. So in your field, do people like try to come up with some statistical description, some universal results, which are like invariant? Like if you find something in South America, you can apply similar features in somewhere in Madhya Pradesh, for example. So I'm saying like, can you like bypass the difficulties of opening new centers or new these observatories and just work with the data that already exists and try to make predictions and test locally, and if it works then you can like, I mean it's a easier thing to do.
Yeah, within India we are trying to do this, to study the commonalities, and that's why we are not advising for like pan-India observatories, but sit together, identify the key gap areas where we actually have to install. Second thing is, it is not just the geology. I mean, geology is one gradient, but then you also have this climatic gradient, which is also a very strong driving factor for much of this changing, including the weathering processes. Okay, that will be entirely different in a temperate country than in a tropical country like ours. So that is one point, like the highly variability in monsoon systems, which doesn't exist in, for example, France. That's why French team came here to set up an observatory to see how it can be compared to there. So within India, we have a consortium of critical zone observatories, and we discuss to see how these are commonalities and how one approach can be tested. For example, this concept of vegetation as a sensor, we tested in France. I was doing postdoc in France, and we tested it there, and it worked well, because that has to do with the soil and water. And your soil and water is coming as a rainfall. So that did not make much a difference for, I mean, the methodology-based hypothesis which is not making a difference, but they have their own set of observations. We have set of observation, we tried, and it is fine, it's working. So some of these hypotheses can be tested, like we have been in touch with the German Terreno Observatory to test the machine learning things, how to get these subsurface spatial hydraulic properties using their data set. So that, I mean, we haven't worked with any US observatory, but with European observatories, we are working on that, sir.
Thank you.
Anybody? No? Anybody wants to ask a question? Okay, thank you.
So if there are no further questions, let us thank Dr. Srilash for an insightful and interesting talk on geology like this. So this is small token of appreciation from Resonance Journal. Yeah, thanks for coming.
We'll break for tea. After that, we'll have something very interesting. I hope this will be useful to you. We'll have groups of people, speakers, and other people from Resonance. And you can make your own groups, 3-4 groups, maybe 4 groups. And we can meet us and kind of converse about what it is to be a scientist or what career. Wow. You have any questions you can ask. You feel free now. If you're shy earlier, this is the way to do it. Okay, let's go for tea now. Yeah. Yeah, here only tea. We'll meet here only. Yeah, here only we'll meet. And there is no nature walk today. Nature walk is in the morning tomorrow, 6:30. Announcement will be made later. 6:30 in the morning tomorrow, possibly. Shared later, yeah.
Before we do so, this evening as well, we will have the Science Activity Center visit. Those who did not make it yesterday, and those who could not come to the Central Instrumentation Facility can join for another tour there. Yeah, thank you. For the Central Instrumentation Facility, right after this session, and for the Science Activity Center, it is at 6 o'clock till 7:30. No, interaction goes on. It is after the interaction.
of things
Hmm.
that have to be explained.
That's what I will just explain to them. Hmm. So, good afternoon. I hope all of you had tea and samosa. And so, we have a plan now about how to do this. So, we have arranged chairs outside where we had tea. Maybe 2 of us will sit at a particular table, and some of you can form groups and come and interact with them, ask them questions, feel free to ask whatever. And then after spending some time with, you can move to another table. Okay, we'll be at perhaps 6 tables. Okay, so you can just feel free to choose your table, but if it's too crowded, you can, you choose another one, you can come back to this one later. Is that okay for everybody? So if you're interested in biology, you might want to only meet a biologist, but do meet other people also. You don't never know. Okay, so yeah, so around if some table is too crowded for a lot of time, other people would also like to ask the same person some questions. So I would kind of signal that you move to another table. Okay. Do that, okay? Okay then, so let's, I think we can go out now already. Just outside where we had tea.